Mars hung in silence in the darkness as a three-eyed Atlas, an alien from the stars, rushed by. The orbital camera opened its eye and glimmered at something mysterious. No sparkling veil of dust, no comet's crown of light, just a faint ghostly blur, so alien that even seasoned astronomers felt uneasy. The response was immediate. Like a precious gem, the mission to study the atmosphere was redirected to observe this phenomenon. What secret demanded such haste? What does this blur in the abyss really mean? Today we will follow a chain of mysteries hidden in this first image, and if you stay with me, you will understand why it should not look this way and why it matters more than anyone acknowledges. Part 1.
Is that even
The
possible?
title and what just happened.
It's
On March 27, 2025, the European Space Agency published an image that should not exist. Not because the technology failed or the observation window closed, but because what appeared in those pixels contradicted almost everything astronomers expected from the comet passing through the inner solar system. The image was captured by the ExoMars Trace Gas Orbiter, intended for analyzing Martian methane, not for photographing visitors from other stars. And yet it was there. A blurred point hanging against the darkness, captured after layering dozens of long exposures because the target was 100,000 times dimmer than the surface of Mars. The observers were struck not by what the image showed, but by what it did not show. There was no tail, no wide cloud of dust and gas stretching millions of kilometers behind the core, no glowing arc trailing the comet in space. Only a compact ball of light, blurry and strangely symmetrical, hovered in the frame, as if something had forgotten how comets were supposed to behave. For reference, comets, according to textbooks, develop tails when they approach the sun. Solar radiation heats their icy surfaces, sublimating frozen substances into space and carrying away particles of dust. The solar wind then pushes this material away from the nucleus, creating the magnificent tails we associate with comet visits. The three-eyed Atlas was meant to do just that. It is an interstellar comet, the third confirmed visitor from outside our solar system, discovered in July 2025 by the Atlas Observation Network. Its trajectory confirmed that it originated from elsewhere. An object ejected from another star system millions of years ago is now passing through our cosmic neighborhood at a speed of 86 kilometers per second. When he reached the distance to Mars, about 228 million kilometers from the Sun, any respectable comet should have been noticeably active, its tails billowing behind it like a banner announcing its presence. However, the three-eyed Atlas arrived quietly and without a tail, at least in the images obtained from ExoMars. The core itself remained unresolved, meaning that the spacecraft could not distinguish the solid body from the surrounding coma, the gas and dust envelope that usually surrounds active comets. All the tools of the European Space Agency could only confirm that something truly exists, a faintly glowing entity exhaling a coma without bothering to form a tail. Astronomers expected a spectacle, but instead encountered a mystery. Avi Loeb, an astronomer from Harvard, warned that this could happen. In a series of publications that appeared weeks before observations of Tri-Eye Atlas, Loeb outlined the anomalies he noticed in the object's behavior. Unusual fluctuations in brightness, possible directed ejection inconsistent with solar thermal patterns, orbital characteristics that did not quite fit standard comet models. Loeb formed his opinion here. He is known for suggesting that Oumuamua, the first discovered interstellar visitor in 2017, could be artificial, possibly a light sail or umbrella from an extraterrestrial civilization. The scientific community largely disagreed with him, preferring natural explanations like nitrogen icebergs or hydrogen emissions. But Loeb's willingness to consider exotic options made him a key voice in issues beyond traditional comet theory. Therefore, when Tri-Eye Atlas appeared, looking nothing like predicted, Loeb's warnings became relevant. The main mystery formed into a single question that is hard to answer. Why does this object not look like a comet when everything about its trajectory and composition suggests it should? Is it just an observational coincidence? Perhaps the tail exists, but it is directed right at us or away from us, making it invisible? Or are we witnesses to something truly strange, an object that cannot be classified because it does not fit into familiar natural frameworks? Yes, I added fuel to the fire of speculation by announcing something unexpected. The agency reported a redistribution of tasks for JUICE, the ice moon researcher of Jupiter, a flagship mission costing €1 billion, currently heading to Jupiter for side observations of Tri-Eye Atlas. Think about this for a moment. JUICE was not intended for studying comets. Its instruments are aimed at the surfaces of icy moons and Jupiter's magnetosphere. Redirecting such a mission, even for a short time, required significant planning, risk assessment, and justification. The fact that this was deemed appropriate indicates that the agency recognized something unusual, significant enough to deviate from the mission parameters. The European Space Agency's statement accompanying the announcement of the redistribution used cautiously neutral language, emphasizing that the observation came as a surprise to everyone. This is a bureaucratic way of acknowledging that Tri-Eye Atlas surprised the scientific community. This urgency hints at something deeper. Perhaps the initial data revealed characteristics that required immediate further investigation. Maybe the lack of a tail raised concerns that this object might not be what it seems. Or perhaps the scientists simply realized the rare opportunity to study an interstellar visitor using several spacecraft simultaneously. Speculations arise. If you were a highly advanced civilization wanting to send a probe to observe other star systems, how would you design it? Perhaps you would cover it with ice and dust, disguising it as a natural object. Perhaps you would minimize reflective surfaces to avoid detection until the last moment. Perhaps you would design it to emit gases in a controlled manner, creating a comet for additional camouflage while avoiding a revealing tail that would expose your activity. This, of course, is pure speculation, intriguing, but unconfirmed. Nevertheless, the question remains, as the data defies simple, natural explanations. The anomalies are not just photographic curiosities. They encompass spectroscopy, polarimetry, dynamics. Each measurement seems to add another layer of strangeness rather than resolving the mystery. And it is here that this story begins, at the intersection of what we observe and what we expected to see, between the soothing predictability of celestial mechanics and the unsettling reality that sometimes the universe presents objects that do not conform to the textbook. What happens when data contradicts theory? What do we do when an interstellar guest refuses to comply? These questions will determine everything that follows as we delve into dimensions, disputes, and the intriguing possibility that 31 atlases represent something beyond our current understanding of comets, debris, and the drift between stars. Part 2. Chronicle of Observations up to the present time. The story of 31 Atlas begins not with a mysterious image, but several months prior, when robotic telescopes systematically scanned the Earth's sky in search of threats and curious objects. On July 1, 2025, the Atlas system for warning about ground impact asteroid strikes detected a moving object that did not match known asteroids or comets. Within a few hours, preliminary orbital calculations revealed something unusual. It was not an inhabitant of the solar system. Its speed vector and trajectory indicated interstellar origins, making it only the third confirmed visitor from beyond to pass through our cosmic yard in all of observation history. The discovery sparked immediate interest in the astronomical community. Interstellar objects are extremely rare, or rather, their detection is incredibly difficult. They move quickly, appear faint, and provide limited observation windows before disappearing back into the darkness between the stars. Oumuamua surprised everyone in 2017 by leaving the scene before detailed studies could be conducted. Tu and Borisov provided the best data in 2019 but raised new questions about the diversity of comets. Now, 3 points of data provided by Atlas have allowed us to refine our understanding of what is ejected from other planetary systems and how these objects behave during their brief passage through the solar system. Observations using the Hubble telescope began almost immediately after confirming its interstellar status. The aging observatory, despite its decades in orbit, is still capable of amazing photometry and spectroscopy. The first images showed a dim object surrounded by a faint coma, a promising sign of the activity of 3 Atlas, sublimating volatile substances as it approached the inner part of the solar system. However, something strange appeared in the color indices. These brightness ratios, measured through different filters, show the composition and reflectivity of the object. The colors did not quite match typical comets, slightly shifting into the red area, hinting at dust properties or composition different from what we observe in solar system comets. Then the James Webb Telescope directed its infrared gaze at the visitor. The newest and most powerful observatory of humanity excels in spectroscopy, breaking light into component wavelengths to identify chemical signatures. Initial spectra revealed something astonishing. Carbon dioxide predominated in the gas mixture 8 times more than water vapor. This inverted ratio is unusual, Most comets we studied show water as the main volatile substance, while carbon dioxide takes a secondary role. Comets are often described as dirty snowballs, emphasizing the water ice that makes up their main mass. But the three Atlas moons seem to predominantly emit carbon dioxide, indicating either an unusual composition or an unusual sublimation dynamic due to their interstellar origin. As summer turned to early autumn, the Atlas III spacecraft continued its journey inward, passing Mars's orbit in early October 2025. This proximity created an unprecedented opportunity. There are several orbital spacecraft on Mars, such as NASA's Mars Reconnaissance Orbiter and MAVEN, ExoMars for gas tracking, and Mars Express from ESA, all equipped with cameras and spectrometers. These spacecraft were not designed to observe comets, but mission planners realized the opportunity to capture an interstellar visitor from a unique perspective. Observations were scheduled, telescope timing coordinated, and targeting maneuvers calculated. ExoMars was designated for high-quality imaging using its CAS camera. The problem was obvious. CAS was designed to photograph Martian surface features like cliffs, craters, and ravines, targets that reflect a significant amount of sunlight and provide high contrast. In comparison, the three Atlas moons were 100,000 times dimmer. Capturing any usable image would require extreme tension on the instrument, layering several long exposures to create enough signal above the noise level. The process resembled the methods of astrophotography used by enthusiasts to capture deep space objects, but it was carried out by a spacecraft orbiting another planet and tracking a moving target millions of kilometers away. While the spacecraft maneuvered, ground telescopes provided constant monitoring. As with the measurements of curves, tracking changes in brightness over time showed a periodicity of 16 hours, indicating that the core rotates every 16 hours, spinning in space with slight changes in brightness that hinted at its elongated shape. These observations were made by observatories scattered across the Earth, coordinating their actions through informal networks where astronomers exchange data in almost real time, understanding that interstellar visitors require collective efforts due to their fleeting nature. Throughout this time, Avi Loeb provided constant commentary through publications and interviews. He noted the absence of a visible tail, even as Tri and Atlas approached distances where sublimation should intensify. He wondered about the behavior of brightness, suggesting that the object might be larger or more reflective than standard comet models predicted. He drew parallels with the anomalies of Oumuamua, building arguments that interstellar visitors systematically defy our expectations, possibly because they are formed under conditions different from the usual, or perhaps he left it unspoken but implied that not all of them are natural. The audience watched the events with interest, heightened by the recent story. Oumuamua captured the imagination precisely because it seemed so strange. Its elongated shape, rotation, and mysterious acceleration away from the sun without visible gas ejection. Debates about its nature moved from scientific journals to mainstream media, with headlines questioning whether we have discovered our first interstellar artifact. Two individuals, I and Borisov, brought some relief with their usual behavior, but also disappointment. Where was the exotic chemistry, the anomalous behavior, a hint that something truly alien had visited us? Three and Atlas seemed ready to find a golden mean, active enough to be clearly associated with comets, and strange enough to fuel speculation. By the end of March 2025, anticipation grew ahead of the publication of images from ExoMars. Preliminary reports indicated that the observation was successful despite technical difficulties, and that gases had detected something amidst noise and weakness. When the European Space Agency finally released the images, the astronomical community gathered around computer screens, waiting to see the comet doing what comets do: sublimating, streaming, leaving its ion trail in the solar wind. Instead, they saw a compact tailless object, blurred and mysterious, refusing to respond to commands. This timeline reveals something important about modern astronomy. We live in an era where discovery happens quickly, but understanding evolves slowly. For several hours after the opening, we learned that Tri-I Atlas is an interstellar object. Over several days, the spectra revealed unusual chemistry. Over several weeks, the curves characterizing its rotation became clearer, but after several months, important questions remain unanswered. Is this a comet or something else? Why does it look strange? What does its composition say about its origin? These questions remain because the data alone does not provide understanding. Interpretation requires models, comparisons, discussions, and often years of analysis before consensus is reached. And now, With an image from the European Space Agency showing an object that is hard to classify, the timeline shifts into a new phase. The mystery deepens rather than resolves, anomalies accumulate instead of clarifying, and the likelihood that Atlas's three eyes represent something truly unusual, be it a natural oddity or something more provocative, shifts from marginal speculation to a legitimate scientific question. What will happen next depends on observations that are still planned, data that is still being analyzed, and debates that are ongoing in conference halls and comments throughout the astronomical community. Part 3. The ESA image, ExoMars, what it actually shows and what it does not. The image of Atlas's three eyes, captured by the ExoMars orbital spacecraft, consists of several overlapping exposures, each lasting several seconds, combined to form a signal above the instrument's noise threshold. What emerges from this overlay is a faint point of light, not quite resembling a star, slightly blurred, distinctly elongated, moving against the backdrop of stars during a sequence of observations. The core itself remains unresolved, indicating that the camera could not separate the solid body from the surrounding coma. All we see is a shell of gas and dust, a diffuse cloud that stretches possibly hundreds or thousands of kilometers from what is at the center. The most striking absence is the tail. Comets develop two types of tails as they approach the sun. A tail of dust forms when sunlight pushes dust particles away from the comet's nucleus, creating a curved arc that follows the comet's orbital path. An iron tail forms when solar wind, a stream of charged particles from the sun, strips ions from the coma and pulls them directly away from the solar direction, creating a bluish glow that can extend for millions of kilometers. Both tails must be visible for the active comet at the distance of Mars, given a reasonable speed of dust and gas ejection. However, Atlas's three eyes showed none. The coma appeared symmetrical, compact, without any elongations or directed streams. There was neither a faint blur indicating the opposite direction from the sun, nor a thin arc tracing the comet's movement. It was just a blurred object that could pass for an unresolved galaxy, or nebula, if you didn't know what you were looking for. As analysts carefully study the data, applying various image processing methods to enhance weak structures, but the tail has not appeared. If it existed at all, it was either below the detection threshold or directed precisely towards or away from the spacecraft, rendering it invisible due to geometry. The tails of comets matter because they serve as diagnostic tools. The amount of dust in the tail indicates the production speed and how much material is lost every second. The shape of the tail indicates the size and speed of the particles. The chemical composition of the tail, determined by spectroscopy, helps identify which molecules sublimate and in what proportions. Without a visible tail, astronomers lose a significant part of their ability to characterize the comet's activity. They are forced to rely solely on whom, complicating the task as it may be optically dense, hiding the core, mixing several sources of radiation, and varying depending on the angle of view. Technical limitations complicate interpretation. ExoMars Cassis works at wavelengths optimized for studying the surface of Mars, not for weak cometary radiation. The dynamic range and sensitivity of the camera, while excellent for the primary mission, struggle with objects that are 10,000 to 100,000 times dimmer than ordinary targets. The noise becomes significant. Random fluctuations in the detector's pixels can mimic weak structures or hide real features. Overlaying multiple exposures reduces but does not eliminate this noise. The missing part of the tail may simply be below the threshold of detection, invisible not because it is absent, but due to the signal-to-noise ratio being too low for its identification. Nevertheless, the symmetry of the coma raises concerns. Even if the tail itself is invisible, one would expect some elongation, a hint of direction in the outer regions of the coma, where gas and dust transition from a connected to a disconnected state, where solar radiation begins to repel particles. The coma appears almost spherical, which may indicate extremely low production speeds, so low that particles hover near the nucleus instead of rushing away, or an observation geometry that perfectly conceals any asymmetry. Both explanations are possible, but require specific conditions, which seem strained. The compactness of the comet's tail adds to the mystery. Typical comet tails extend far beyond the nucleus, often tens of thousands of kilometers wide, with brightness that gradually diminishes with distance. The coma in the Atlas of Three Eyes appears denser and more concentrated, as if gas and dust do not disperse as effectively as expected. This may indicate unusual gas speeds, possibly that the sublimation of carbon dioxide leads to slower expansion than water. Or it may signify unusual properties of dust, particles that clump together or become electrically charged, altering their dynamics. The public reaction to the image was immediate and predictable. Social media was flooded with comparisons to Oumuamua, which also lacked a tail and sparked speculation about artificial origins. The word alien often appeared in the comments, although the ESR carefully avoided such terminology in official statements. Scientists emphasized technical complexities and observational limitations, urging patience and caution. However, the strangeness of the image was undeniable. This does not resemble what a comet should be, at least according to models and expectations based on decades of studying the comets of the solar system. However, astronomers discuss another possibility, albeit reluctantly raising it to the level of a hypothesis without additional evidence. What if the object 3 Eyes of Atlas is not a comet in the usual sense? What if it is a solid body, perhaps rocky, mixed with ice, which weakly emits gases, forming a comet without the active sublimation process needed to create a tail? This makes it more like an asteroid than a comet, although the difference blurs on interstellar scales, where objects may not fit into familiar categories of the solar system. The object Oumuamua faced similar debates about classification, ultimately being designated as a comet by some and as an asteroid by others, while many remained undecided. The upcoming observations with JUICE are of significant importance as they provide another perspective, a set of tools, and the opportunity to capture the formation of a tail if it is delayed or occurs periodically. JUICE will observe the 3 Eyes of Atlas at various distances from the Sun, under different angles and wavelengths. If a tail appears, it will resolve the mystery towards natural explanations, possibly hidden by the geometry or time from ExoMars. If the tail remains absent, the anomaly will only deepen, demanding more creative explanations for why the object, clearly emitting gases, refuses to demonstrate the characteristic feature of cometary activity. Speculations inevitably lean towards more provocative explanations. If the 3 Eyes of Atlas were artificial, a probe, a sail, or outdated technology, how would we expect it to look? Probably not like a sleek spaceship from science fiction. Most likely, it would be covered in dust accumulated over millions of years of interstellar travel, possibly intentionally camouflaged, or perhaps just naturally weathered by micrometeorite impacts and cosmic rays. He could emit gases from volatile substances on its surface or interior, creating a comet that conceals its true nature. He might not have a tail if his gas emissions were caused by internal processes rather than solar heating, which do not align with the anti-solar direction where tails form. This is merely a bold speculation, entertaining, but unproven. The scientific consensus remains that natural explanations are much more likely. Comets are common, as are interstellar ejecta. Unusual compositions are expected, given the diversity of planetary systems throughout the galaxy. Attracting attention to artificial origins requires outstanding evidence, not just anomalies, but anomalies that refute natural explanations, combined with positive signs of artificiality, such as geometric structures, coherent signals, or impossible materials. Nevertheless, the image remains, refusing to fit expectations and challenging conventional ideas of what interstellar visitors should look like. Perhaps this is the main message, the main lesson we can learn from the ExoMars mission. Our models are based on limited data, and each new interstellar visitor will reveal something unexpected. The galaxy is stranger and more diverse than we could expect based on our provincial experience within the solar system. The comet's tail may appear tomorrow, bringing everything back to normal, or it may not appear at all, leaving us with the mystery of an object whose behavior is unusual enough to maintain interest and preserve an intriguing gap between what we observe and what we understand. Part 4. Redirection of the JUICE mission, why it is important. The researcher of Jupiter and its icy moons was not originally supposed to deal with comets. JUICE was launched in April 2023 with the sole purpose of exploring Jupiter's icy moons, Ganymede, Callisto, and Europa, searching for subsurface oceans, analyzing surface compositions, and mapping magnetic fields. The spacecraft carries 11 instruments optimized for planetary science at distances from Jupiter, rather than for studying comets in the inner solar system. His trajectory includes a complex cruise with several gravitational maneuvers before reaching Jupiter in the year 2031. Each maneuver is planned years in advance, with specific time allocated for each observation window and every fuel source meticulously accounted for according to mission objectives. When the European Space Agency announced the redirection of JUICE to observe Comet 3I Atlas, it surprised the community of space research scientists. It was far from a trivial decision. Redirecting the flagship mission involves risk assessments, engineering checks, tool calibrations, and most importantly, justification. Why spend resources on an object that exceeds the primary mission? What is the scientific value that justifies the operational complexities? ESA's readiness to proceed with this step signals something important. The agency has recognized the 3I Atlas as an opportunity that cannot be ignored, despite the costs and complexities. Circumstances have favored JUICE. The spacecraft is currently moving through the inner part of the solar system during its first flyby past Earth, passing relatively close to the trajectory of 3I and Atlas. The observation will not require significant maneuvers, just adjustments in orientation to aim the instruments at the target. The distance will be significant, millions of kilometers, but the JUICE cameras and spectrometers are designed to operate on planetary scales and can capture details that ground-based telescopes cannot. The observation window will last several days, allowing multiple passes and different angles of view as both spacecraft and the comet move in their orbits. What can JUICE provide that other observatories cannot? Firstly, a multi-layered shot that captures the comet and its potential tail simultaneously in the visible and near-infrared ranges, revealing color gradients that help determine the composition of dust and particle sizes. Secondly, spectroscopy using tools like MAGIS and UVS for a more detailed analysis of the coma's chemistry than was possible in previous observations. Time series for tracking tomato brightness, changes that may correlate with rotation or episodic gas emissions. Polarimetry measuring how light scatters from comet dust provides clues about the structure and composition of particles. The symbolic significance should not be underestimated. The operations of the European Space Agency with a mission costing €1 billion are not taken lightly or impulsively. The decision to reassign the JUICE mission reflects an institutional assessment that the object known as the 3-eyed Atlas requires serious scientific attention. This is a voice of trust in the importance of the object, a signal to the broader scientific community that this is not just public curiosity or media hype, but a legitimate target for flagship-level resources. When the official statement from the European Space Agency characterized the observation as unexpected for everyone, the subtext was clear. We were surprised, we take this seriously, we are allocating top-level resources because there is something here that deserves it. Past missions to comets provide context for what JUICE can achieve, even from a distance. The Rosetta mission, which orbited Comet 67P Churyumov-Gerasimenko for 2 years, revealed complex details of cometary geology, gas emissions, and evolution. The Deep Impact mission collided with Tempel 1, exposing subsurface ice and investigating ejected jets. Stardust collected dust samples from Wild 2 and returned them to Earth for laboratory analysis. These missions changed our understanding of comets, transforming them from astronomical abstractions into complex dynamic worlds. JUICE won't be able to reach such a level of detail with a 3-eyed Atlas. The distances are too great and the exposure time is too limited. But even rough characteristics will significantly advance knowledge. The specific scientific questions that JUICE can explore are intriguing. Will the tail become visible from another angle, solving the riddle of simple geometry? Will the chemistry of the coma change as the comet approaches perihelion, showing how interstellar ice compositions react to solar heat? Will there be unexpected outbursts? Perhaps there are molecular species that have never been observed in the comets of the solar system. Traces of exotic chemistry from the dense disk environment where the 3-eyed Atlas originated. Will polar symmetry confirm or refute the unusual properties of dust proposed by previous measurements? There is also the possibility of detecting delayed or episodic activity. Comets do not always behave smoothly. They can exhibit sharp bursts when sublimation accelerates rapidly, possibly due to pressure buildup beneath the surface, ice cliff collapses, or rotation bringing fresh material to light. If the 3-eyed Atlas is at the edge of visibility, barely active enough to create a tail, but not active enough for clear formation, a sudden increase in activity can lead to dramatic changes observed by JUICE. The tail can ignite like light, turning the object from an anomaly into an ordinary comet in just a few hours. Speculations about the inner motives of the three-eyed atlas become increasingly intriguing. The agency was not required to make the change in observation tasks for the object JUICE public. Many observations of cosmic objects are planned discreetly, with data becoming available in archives after weeks or months without much noise. However, ESA decided to announce this, indicating a desire to attract the attention of the scientific community. Perhaps this is done to coordinate actions with other observatories, maybe to manage expectations regarding the main JUICE mission schedule, or perhaps to demonstrate readiness to respond to new scientific opportunities. This publicity itself is an important signal indicating the significance of the three-eyed atlas, justifying its openness. There is also a competitive aspect, although scholars rarely discuss it publicly. Several agencies and observatories are monitoring the three-eyed atlas: Hubble, the James Webb Telescope, ground telescopes around the world, and Martian orbital spacecraft. The ESA's decision to include JUICE in this observation guarantees Europe's high-level participation, ensuring data rights and authorship positions in future articles, while also supporting ESA's image in interstellar object research. Space agencies work together, but also recognize the importance of visibility and scientific recognition. Observations from JUICE will lead to publications with an ESO author list, conference presentations, and press releases highlighting Europe's contribution. The audience reacted positively to the announcement of task redistribution. People understood that if the billion-dollar mission to Jupiter was being redirected, something truly interesting was happening. The narrative shifted from scientists showing mild curiosity to a desire for observation. This urgency, whether real or perceived, heightens the sense that the three-eyed atlas is unique, that any anomalies appearing in the initial data require immediate attention, and that the window for understanding may quickly close if we do not mobilize resources now. What JUICE will ultimately reveal remains uncertain and depends on the geometry of observation, the functioning of the instruments, and the behavior of the object. The optimistic scenario suggests that JUICE will obtain clear images showing tail formation, spectroscopy confirming typical comet chemistry, altered by interstellar heritage, and polar images explaining dust properties through natural mechanisms. These observations will help dispel the mysteries of the three-eyed atlas, categorizing it as an interesting natural object and closing the door to exotic speculations. A pessimistic scenario, perhaps conversely, depends on your desire to unravel the mystery, suggesting that JUICE will confirm anomalies by showing a tailless object with unusual chemistry and dust properties that defy simple explanations, deepening the enigma rather than resolving it. In any case, the fact that ESA deemed this observation necessary speaks volumes. The agency does not pursue every astronomical curiosity with costly missions. Resources are limited, competition for observation time is fierce, and justifications must be stringent. This spacecraft JUICE, which has become the focus of intense attention, caught the interest of European Space Agency staff due to preliminary data indicating that it contains something worthy of further study. Scientists managed to convince the leaders that the scientific results justify the complexity of the operations. Whether this decision will validate their warnings or prove too cautious will become clear in the coming weeks when JUICE data begins to arrive, and analysts start the meticulous work of extracting signal from noise, truth from artifacts, and understanding from observations. The fifth part will discuss the anomalies related to Avi Loeb's research and their significance for a new image. Avi Loeb has never hesitated to ask uncomfortable questions. A Harvard astronomer built his early reputation on mainstream astrophysics, black holes, and the cosmology of the early universe, the first stars, before shifting to technosignatures and the search for extraterrestrial intelligence. His 2018 article, in which he suggested that Oumuamua might be an artificial rather than a natural object, made him both a famous and controversial figure, eliciting excitement from proponents of bold ideas and criticism from those who value caution. When the object known as the three-faced atlases appeared, Loeb was ready to explore it for anomalies, publishing a series of posts documenting the oddities visible even in preliminary data. The first anomaly that Loeb noticed was the absence of a tail, even in early ground observations. Most comets typically show at least a weak tail development by the time they cross Mars's orbit, if they are actively sublimating. However, the three atlas images showed nothing like that. Some observers reported a possible slight elongation in certain images, but nothing definitive that couldn't be attributed to noise or processing artifacts. Loeb noted that this absence aligns with the behavior of Oumuamua. another interstellar visitor that did not produce a visible tail despite its close passage to the Sun, where any ice should actively evaporate. The second anomaly concerned what Loeb termed the front ejection. Detailed astrometric measurements and precise tracking of the positions of three celestial atlases against the star background showed slight deviations from purely gravitational motion. These non-gravitational accelerations are often observed in comets, caused by gas emissions from a rotating core, acting like tiny rocket engines, slightly diverting the object from its predicted path. However, the direction of the acceleration of the three Atlas figures did not coincide with the anti-solar direction, where one would expect maximum heating and sublimation. Instead, it seemed to be directed forward, as if something was pushing the comet along its trajectory, rather than perpendicular to it. This is important because the natural gas emissions during solar heating should produce forces roughly perpendicular to the Sun-comet lines if the core is rotating, and emissions occur from different locations as various regions come under sunlight. Acceleration directed forward is harder to explain naturally, as it requires specific combinations of the axis of rotation, orientation, and positioning of the emissions, which seem forced. Loeb suggested that this might indicate controlled movement, which is a provocative claim, lacking direct evidence, but aligns with his overall willingness to consider hypotheses of artificial origin. The third anomaly concerned brightness and cross-section. The object, Three Eyes of Atlas, turned out to be brighter than expected for a comet of similar size, which may indicate that its core is larger than initially thought, its albedo higher than typical comets, or that light scattering from the coma is unusually effective. Loeb noted that brightness anomalies can arise from geometric effects. A flat object, like a sail, reflects more light than a sphere of the same mass, or from active surface coatings that enhance reflectivity. He did not claim that this proves artificial origin, but emphasized that the brightness exceeding forecast requires explanation, especially in conjunction with other anomalies. The fourth anomaly concerned orbital geometry. The trajectory of Three Eyes of Atlas brings it closer to the plane of the ecliptic, where the planets of the solar system rotate. Unlike previous interstellar objects, Oumuamua approached the ecliptic at a nearly perpendicular angle, like two other objects, consistent with random arrivals from any direction in space. The trajectory of Three Eyes of Atlas near the ecliptic is statistically less likely compared to random chance, though not impossible. Loeb suggested that this might indicate a purposeful arrival, an object whose trajectory was deliberately chosen to pass through a region where planets and potential civilizations are concentrated. Now, we can assess how the ExoMara image relates to these anomalies. The absence of a visible tail directly confirms Loeb's first observation, adding credibility to his early warnings that the Three Eyes of Atlas is behaving abnormally. The compactness and symmetry of the coma align with low or absent emissions, corresponding to the second anomaly of unusual acceleration directions. The unresolved core does not allow for a definitive check of the brightness anomaly, but the faintness of the coma, despite the expected activity, supports the idea that something in the production or scattering of light from this object is different from ordinary comets. It is important to note that the consistency of anomalies does not equal proof of artificial origin. There are many natural explanations for each peculiarity. The absence of a tail may be related to geometry or low emission rates. Acceleration forward may result from specific rotational configurations. Brightness may reflect variations in albedo or properties of dust. Orbital geometry may be a random coincidence. Since only 3 interstellar objects have been discovered, we have no grounds for strict statistical assertions about typical trajectories. Scientific criticism of Loeb's interpretations was active but respectful. Most astronomers acknowledge the anomalies while preferring natural explanations. Scientists note that weak tails may be hidden by observational limitations, a signal-to-noise ratio below the detection threshold, background contamination from stars or galaxies, and temporal changes when the tail only appears periodically. They emphasize that the unusual does not mean impossible, and nature often creates astonishing configurations without the intervention of intelligence. The tension between public perception and scientific caution creates an interesting dynamic. Society, prepared by decades of science fiction and recent headlines about Oumuamua, longs for contact with aliens. Every anomaly is interpreted as potential evidence of extraterrestrial technology. Every unusual measurement spawns speculation about probes and artifacts. Scientists, accustomed to exhausting natural explanations before making extraordinary claims, restrain this urge for cosmic significance. They see low signal-to-noise ratios, complex systematics, and insufficient measurements to draw firm conclusions. Loeb occupies a unique position in this dynamic. He has enough qualifications to be taken seriously. A Harvard professor, hundreds of peer-reviewed articles, head of the astronomy department, yet he is willing to publicly speculate in ways most scientists avoid. His posts and interviews provide speculations that major scientific journals do not publish. Those what-if narratives that capture the public imagination. Critics accuse him of seeking attention, undermining the reputation of astronomy by giving credence to strange ideas. His supporters praise him for asking questions that others fear, for expanding horizons and encouraging openness. The significance of Loeb's participation in the three-eyed atlas research lies in the fact that his previous warnings now appear predictive. He spoke about the need to pay attention to the absence of a tail, and the ExoMars confirmed this. He noted the unusual brightness, the unresolved core, and the faint coma, which supports the ongoing mystery. He suggested that the acceleration might not be solar, and the astrometric analyses remain uncertain. Do these facts confirm his skepticism regarding natural explanations or simply demonstrate good observation skills? It depends on your beliefs about extraordinary claims and extraordinary evidence. In the following sections, we will delve into the data highlighted by Loeb. Spectroscopy revealing chemical anomalies, polarimetry showing unusual light scattering, dynamics that do not fit standard models. Each dataset adds details to the mystery, either resolving anomalies through natural mechanisms or combining them into a pattern that requires explanation. The question is not whether three-eyed atlas is strange. That is obvious. But whether this strangeness reflects a natural diversity we have not yet encountered, or something truly beyond our current understanding of cosmic debris. As shown by the image from the European Space Agency, sometimes the most important observations lie not in what they reveal, but in what they clearly do not show, like a story that is missing, like a guest who looks almost right, but not quite, like a puzzle piece that won't fit no matter how hard you try to force it. Part 6. Spectral and compositional clues. Chemistry tells stories that images cannot reveal. When the James Webb Space Telescope aimed its spectrograph in the near-infrared range at the three-eyed Atlas comet in September 2025, it was not searching for tails or nuclei, but analyzing light by breaking incoming photons into constituent wavelengths to determine which molecules were present in the coma and in what proportions. Spectroscopy is the most powerful diagnostic tool in astronomy, capable of revealing temperature, composition, speed, and even the strength of magnetic fields, all encoded in patterns of bright emission lines and dark absorption features scattered across the electromagnetic spectrum. What James Webb discovered immediately caught attention. Carbon dioxide dominated the emissions of the coma 8 times compared to water vapor. In contrast, typical comets of the solar system show the opposite ratio, where water usually predominates, making up 60 to 80% of the sublimating volatiles, while carbon dioxide and carbon monoxide remain secondary. This inverted relationship is unusual, but not unprecedented. Several comets in the solar system display carbon compositions, especially those originating from the distant Oort cloud, where formation temperatures differed from the warmer inner regions where most comets formed. However, the three-eyed Atlas is not from the Oort cloud. It is interstellar, formed in the planetary system of another star under potentially radically different conditions. The dominance of carbon dioxide may reflect the chemistry of the parent system, possibly a star with different metal content, varying carbon and oxygen ratios in its protoplanetary disk, and different temperatures in the comet formation zone. Alternatively, this may indicate a preferred loss of water over millions of years that the three-eyed Atlas spent in interstellar space, where cosmic rays and ultraviolet photons from distant stars slowly process surface ice, breaking molecular bonds and allowing lighter molecules like water to escape, while heavier substances like carbon dioxide remain trapped. Spectra also revealed weak signatures of other molecules, carbon monoxide, possibly traces of methane, potential hints of more complex organic compounds. The signal-to-noise ratio in these detections was critical, requiring careful analysis to distinguish real characteristics from instrument artifacts or contamination from foreground sources. But if these findings are confirmed, they will create a picture of chemical complexity, an object bearing not only simple ice, but also potentially pre-organic molecules, organic compounds that under other circumstances could serve as building blocks for life. Dust signatures in the spectrum added another layer of mystery. Reflected sunlight from dust particles in the comet's coma exhibited an unusual red tilt, indicating that longer wavelengths are reflected more efficiently than shorter ones, creating a color shift towards the red end of the spectrum. Comets in the solar system usually exhibit flatter or neutral inclinations, with dust particles reflecting sunlight relatively uniformly across all visible wavelengths. Red tilts may indicate an unusual composition of dust, possibly rich in carbon, organic residues, or iron-containing minerals, as well as non-standard particle sizes, where larger particles scatter light differently than the fine dust typical of most cometary nuclei. Polarimetric observations added another mystery. Polarimetry measures how light is polarized when scattered by dust particles, and the degree and direction of polarization reveal information about the shape, size, and composition of the particles. The European Consortium conducted polarimetric observations of comet Tri-I Atlas using several medium telescopes, tracking how polarization changed with the phase angle as Tri-I Atlas moved along its orbit. The results were astonishing. The comet Tri-I Atlas demonstrated a deep negative branch of polarization at small phase angles, reaching -2.7% at an angle of about 17 degrees. This technical terminology reflects specific scattering behavior. When sunlight hits dust at certain angles, it polarizes in a plane perpendicular to the scattering plane, rather than parallel, as is usually the case. The depth of this negative branch, how negative the polarization becomes, and the angle of inversion at which polarization switches from negative to positive provide diagnostic information about the properties of dust. Most comets in the solar system exhibit negative polarization branches ranging from -1 to -1.5%. The value of -2.7% for Tri-I Atlas significantly exceeds this range, indicating dust properties that go beyond normal distribution. Theoretical models link deep negative branches with highly porous loose aggregates. Dust particles made of small subparticles, loosely bound together and filled with voids, enhancing certain scattering behaviors. Alternatively, unusual polarization may indicate differences in composition, possibly silicate mixtures atypical of solar system dust, or organic coatings altering the surface's reflectivity. The combination of spectroscopy and polarimetric images paints a picture of an object that is chemically and physically different from typical comets. The predominance of carbon dioxide suggests formation in a different environment or processing by mechanisms other than those experienced by comets in the solar system. Unusual dust with a red tint and deep polarization indicates either an exotic composition or unusual structures that do not match our basic understanding developed over decades of studying solar system comets. Some scientists have hypothesized that these differences simply reflect interstellar heritage. After all, we have studied only 3 interstellar objects in detail, which is too small a sample to establish what is considered normal for bodies ejected from other planetary systems. Perhaps every interstellar guest will exhibit chemical and dust properties that deviate from the norms of the solar system, reflecting the diversity of stellar formation conditions, planetary disk compositions, and evolutionary histories across the galaxy. If 3 objects seem strange, it may be because our reference point is limited, focused on the debris field of one star. However, there is a speculative alternative that remains in discussion, no matter how many natural explanations are suggested. What if the unusual dust is actually artificially created? What if the properties of polarization reflect not natural minerals, but manufactured particles? Perhaps these are carbon composites, artificially created aggregates, reflective coatings designed for specific optical properties. This is pure speculation, lacking direct evidence, but it remains in the gap between data and interpretation, posing uncomfortable questions about how we would recognize artificial materials if we encountered them. Spectroscopic detection of organic compounds, if confirmed, fuels speculation. Organic molecules are widespread in space. Amino acids have been found in meteorites, complex hydrocarbons detected in interstellar clouds, and molecular precursors of life discovered on comets and asteroids throughout the solar system. Their presence in 3 objects is not surprising, but it will be intriguing, especially if the molecular composition differs from the organics of the solar system, which could indicate various synthetic pathways, different chemical conditions, and perhaps, although this is a huge leap, different biological origins if the object crosses a system where life exists. The question of dust is directly related to the mystery of the missing tail. If the dust particles are unusually large or have strange optical properties, they may not effectively scatter light in the tail area, remaining invisible despite their physical presence. If the production of dust is dominated by large particles, these particles will return to the core under its weak gravitational influence rather than being carried away by solar radiation pressure. The tail will not form not because sublimation does not occur, but because the dust that forms never escapes the gravitational influence of the core. This natural explanation is elegant and plausible. It does not require exotic physics, no artificial intervention, just unusual yet permissible properties of particles. Many astronomers support this interpretation, considering it the simplest explanation for the absence of a tail and polarization anomalies. However, simplicity is not proof, and the accumulation of unusual yet permissible characteristics, the predominance of carbon dioxide, a tendency for red dust, deep polarization, absence of a tail, linear acceleration, creates an overall sense of strangeness that exceeds what one might expect from random variations. The chemistry of Object 3 and Atlas potentially reveals its birthplace, offering clues about the stellar environment that created it. Recent models, which will be studied in more detail later, suggest that Tri and Atlas originated in the thick disk of the Milky Way, an ancient, metal-poor population of stars orbiting the galactic center, distributed above and below the thin disk where our sun resides. The stars of the thick disk formed between 8 and 12 billion years ago, in an earlier era of galactic history when the interstellar medium had a different chemical composition, fewer heavy elements, and different molecular ratios. If Tri and Atlas indeed originated from the star of the thick disk, their unusual chemistry becomes clearer. Conditions with low metal content give rise to various sequences of mineral condensation, different ice compositions, and distinct organic deposits, unlike the relatively metal-rich environment in which our solar system formed 460 million years ago. The predominance of carbon dioxide may indicate the formation around a carbon star or in a disk, where oxygen was primarily bound to silicates rather than water ice. Unusual dust may be exactly what one would expect from ancient, chemically primitive materials processed over billions of years of cosmic radiation. This context elevates Tri-I Atlas from mere curiosity to treasure. If he really carries fossilized chemistry from the Tolstoy disk, it is a sample of galactic conditions from epochs that we can only study through indirect observations of distant stars and ancient stellar populations. Laboratory analysis of return samples is a goal that currently far exceeds our capabilities but may be achievable in the future, potentially revealing isotopic ratios, mineral structures, and organic molecules that tell stories of what the galaxy was like in its youth and the chemical pathways that existed before the universe was enriched by the products of supernovae from several generations. But for now, we are limited to remote observations, spectroscopy, and polar visualization, as well as images from millions of kilometers away. These tools revealed an object that does not fit conventional categories, accumulating anomalies faster than explanations, enticing with hints of chemical exoticism while remaining without definitive answers. The following observations of the object, starting with data from ground telescopes as 3 and Atlas approaches perihelion, and continuing with Hubble and James Webb campaigns, will either resolve these mysteries through data accumulation or deepen them, confirming that yes, this object is indeed so strange, and no, we do not fully understand why it is so. Part 7. Spin, Light Curve, Dust Activity, and the Missing Story. Objects in space are rarely at rest. They spin, tumble, sway, and change orientation. Their rotation describes complex trajectories in inertial space as internal masses shift and external moments accumulate. For comets, rotation is a diagnostic feature. It reveals shape, controls ejection patterns, and determines how gas jets deflect the object from its gravitational trajectory. Understanding the rotation of Tri and Atlas became a priority for observers around the world, requiring weeks of continuous photometry as the object moved in its orbit, measuring brightness changes that encode information about the rotation. A team led by Spanish scientists published the first detailed analysis of rotation at the end of October 2025. Their data came from several observatories located at different longitudes, allowing for continuous observation as the Earth rotated and avoiding gaps that could complicate the determination of the period. The light curve, with brightness plotted against time, showed a clear periodicity of 16 hours and 16 minutes, with amplitude variations around 0.3 tenths. In simpler terms, 3 Atlas completes one rotation every 16 hours, and its brightness changes by about 30% between maximum and minimum with each rotation. This amplitude reveals information about the object's shape. A perfect sphere would not show changes in brightness regardless of its rotation. From any orientation, it would look the same. Elongated objects display changes in brightness as their cross-section varies during rotation, sometimes showing their wide side and sometimes their narrow side. The amplitude of 0.30 suggests moderate elongation, possibly with an axis ratio of about 1.30 to 1. Not too pronounced. An object shaped like a cigar, similar to was assessed with a ratio of 10 to 1, but differed significantly from a sphere. The rotation period itself is unremarkable for comets. The rotation periods of comets in the solar system vary from hours to days, and 16 hours is comfortably within the average range. This refutes exotic explanations, such as artificial structures that could rotate faster if designed to create artificial gravity, or not rotate at all if using stabilization systems. 3 and Atlas rotates as a natural object should, influenced by the conservation of angular momentum and gas jets that slightly alter its rotation over time. However, the light curve conceals additional complexities. Upon careful examination, subtle deviations from the ideal sinusoidal variation are revealed. Hints of a secondary period, possible brightness fluctuations unrelated to rotation, and periodic sharp changes that may indicate individual ejection events. These deviations are on the edge of the noise background, requiring careful analysis to distinguish real variations from atmospheric distortions, systematic instrument errors, or contamination from background stars that accidentally appeared near the Object 3 and Atlas in the images. If these deviations are confirmed, it will mean that the 3I Atlas is not a simple inert body rotating uniformly. Instead, he actively evaporates substances with changing intensity, possibly with discrete jets that activate when certain areas hit sunlight. This may also be related to the surface features, rocks, pits, cracks, which create localized hotspots of sublimation. This fully aligns with the natural behavior of comets. Missions like Rosetta show that comet nuclei have a complex geological structure, with diverse terrain leading to spatially and temporally variable evaporation activity. Estimates of dust production add another layer of complexity to the task. Analyzing the light scattered by the comet and comparing it with models of dust scattering efficiency, researchers estimated that 3I Atlas loses mass at a rate of between 0.3 and 4.2 kilograms per second. This is insignificant compared to typical comets approaching the Sun. Bright, active comets can shed hundreds of kilograms per second, even tons at perihelion, creating impressive tails visible to the naked eye. Moderate production of 3 and Atlas speaks of low activity, minimal sublimation due to core exhaustion in volatile substances, or that most of the evaporated gas does not efficiently carry dust. The discrepancy between gas release and dust production is concerning. Spectroscopy confirms the presence of gas. Carbon dioxide predominates, water is detected, other volatile substances are present in small amounts, but the dust that should rise with the gas flow as the ice sublimates is practically absent in the tail region. Why does the gas escape without carrying dust with it? There are several mechanisms that can explain this discrepancy. One possibility is related to the size of the particles. If the dust particles are mostly large, millimeter-sized rather than micrometer-sized, they will be too heavy for the gas to accelerate them to the speed needed to leave the core. They may rise briefly, hover, and then fall back, never leaving the core. This would create a body filled with large particles near the core, but without a long tail, as the particles would never reach distances where solar radiation pressure could carry them away. Another possibility is cohesion. If dust particles are sticky, possibly covered with organic substances, or having an electrostatic charge, they can quickly clump together upon release, forming aggregates too heavy to leave the core. This will suppress the formation of a tail while allowing gas to escape freely, creating exactly the situation we observe, an active coma without a tail. Cohesive dust has been observed on other comets, especially those rich in organic composition, so this mechanism has precedence. The third possibility relates to the geometry of observation. If the comet's tail is directed straight towards or away from Earth, it will appear shortened to invisibility, hidden along the line of sight. This explanation is geometrically plausible but statistically unlikely. Orbital mechanics makes the perfect alignment between the tail, the sun, and the observer rare. Moreover, several observatories from different angles could not capture the tail, indicating that it is not just hidden by geometry, but is indeed weak or absent. The rotation of the comet complicates the situation as its core spins, with different areas coming into sunlight, each with potentially different compositions, sublimation rates, and dust formation efficiencies. If only certain areas produce dust, and these areas are positioned so that the emitted dust is not directed away from the sun, then the formation of a tail can be suppressed even with ongoing activity. This requires a specific but not impossible configuration of the axis of rotation, the location of jets, and the geometry of observation. Historical parallels exist but are not entirely satisfactory. Comets, like the previous interstellar one, developed a magnificent tail visible through amateur telescopes, proving that interstellar objects can behave normally. The object Oumuamua had no tail, despite passing significantly closer to the sun than the three-eyed comet, which sparked debates that continue to be discussed. The three-eyed comet occupies an intermediate position, more active than Oumuamua, but less impressive than burrows off. This average position causes discomfort, as an averaging that hides extremes rather than representing typical behavior. Public interests are palpable here, a comet that spins like a clock, ejecting gas into space, losing dust in its coma, but refusing to form a tail. How is this possible? It resembles watching a car with a running engine and spinning wheels but not moving because the transmission is stuck in neutral. All components are present and functioning, but the expected result, forward motion, or, in this case, the formation of a tail, does not occur. This discrepancy between activity and visible results creates cognitive dissonance that no technical explanations can resolve. Speculations about deliberate suppression of activity are tempting, but lack evidence. Could an artificial construct intentionally minimize its reflective signature, releasing gas just enough to match the comet's expectations while avoiding a bright tail that would make it noticeable? Technically, yes, but why? What advantage does invisibility hold for a probe visiting our solar system? If detection itself is not dangerous, perhaps civilizations avoid contact, maybe interstellar law prohibits overt invasions. There is no clear motivation for stealth. And even if such motivation existed, the execution seems imperfect, as we still discovered the Three Eyes comet and are closely studying each of its anomalies. A natural explanation is still considered the most likely by most researchers. Unusual yet permissible properties of particles combined with moderate activity levels could lead to the formation of a coma without a tail. This interpretation does not require new physical theories, does not imply exotic materials or intelligent activity, and fits within the broad spectrum of cometary diversity observed in solar system objects. Although this explanation seems insufficient, leaving questions about why particles have such properties, it does not diminish its significance. Nature is not obliged to conform to our aesthetic preferences for elegant explanations, yet the anticipation grows as the three ocular atlases approach perihelion, the point of closest approach to the sun, where solar heating reaches its peak. If the tail is to appear, it will happen at that moment. Observations with the JUICE spacecraft, coordinated ground campaigns, and space telescopes will monitor the moment when sublimation crosses a certain threshold, and the missing tail will suddenly manifest, streaming behind the core like a fluttering banner. This moment, if it happens, will resolve much of the mystery, but if it does not, if the three-eye atlases pass perihelion still without a tail despite maximum heating, the anomaly will become something requiring more creative explanations than unusual dust or poor angles of view. The next few weeks will reveal whether the three-eye atlases are merely eccentric objects within natural boundaries or something that truly transcends our understanding of cosmic debris. Part 8. Extreme negative polarization and what it implies. Light is a wave, oscillating electromagnetic fields propagating through space at a speed of 300,000 kilometers per second. Typically, sunlight is unpolarized, its oscillations occurring randomly in all perpendicular planes relative to the direction of propagation, without creating a preferred orientation. However, when light is scattered by particles, dust grains, atmospheric molecules, and cometary debris, it can become polarized, with oscillations predominantly directed in one direction. Measuring this polarization allows for information about the particles causing scattering, which is inaccessible by other methods, making polarimetric observations a powerful tool in astronomy. For the three-eyed atlases, polarimetric observations revealed something unusual. The degree of linear polarization, or the fraction of light becoming polarized after scattering, showed a deep negative branch at small phase angles. The phase angle is the angle between the sun, the comet, and the observer, essentially measuring the angle at which you see the reflected sunlight. At angles of about 17 degrees, the polarization of three ocular atlases reached -2.7%, indicating that the light became polarized perpendicular to the scattering plane, rather than parallel to it. This negative polarization is common at small phase angles for many objects in the solar system, but depth matters. Most comets exhibit negative branches ranging from -1 to -1.5%. Some exceptions reach -2%. The three-eyed atlas has a negative polarization of 2.7%, placing it at the extreme limit of observed values and indicating properties of dust that significantly deviate from the norm. The angle of inversion at which polarization shifts from negative to positive with increasing phase angle is about 17 to 18 degrees, which is somewhat unusual compared to typical comets, where inversion occurs in the range of 20 to 30 degrees. What does this mean from a physical perspective? The theory of polarization is complex and involves calculations of multiple scattering for spherical particles, more complex models for irregular shapes, and interactions between electromagnetic waves and the optical properties of materials. However, the general principle is that negative polarization at small phase angles arises from multiple scattering events and coherent backscattering, as light is scattered several times in porous aggregates before escaping. The deeper the negative branch, the more effective this process, which is generally associated with highly porous, loose particles of dust that are more void than solid matter, with fractal structures where fine subparticles are loosely connected to each other. Laboratory measurements of materials similar to comet dust help interpret these observations. Researchers create synthetic dust, mixtures of silicates and organic substances, and measure their polarization properties under controlled conditions. Porous aggregates with over 90% porosity, meaning 90% voids and 10% solid material, show deep negative branches similar to those observed in the three-eyed atlas. These structures are fragile, easily destroyed by collisions or compressive forces, but can be preserved in the soft environment of space, where speeds are low and collisions are rare. Alternative interpretations suggest unusual compositions rather than structures. Some materials, possibly carbon-rich organics or specific silicate mixtures, scatter light with polarization properties different from typical silicates found in the dust of the solar system. If the dust of the Atlas of Three Eyes is chemically exotic, reflecting its interstellar heritage and formation in a high-density environment with various elemental abundances, polarization could arise from composition rather than porosity. There is also the possibility of surface shells. Dust particles can represent structures with a core and mantle, silicates with organic coatings or vice versa, where the mantle dominates scattering properties. Such structures can create unusual polarization without the need for extreme porosity or changes in compositions. Shells are widespread in the dust of the solar system and form when gases condense on the cold surfaces of particles or when energetic processes alter surface layers. Connecting polarization with the missing tail requires some theoretical manipulations, but such paths exist. If the dust particles are unusually porous and loose, they may have low terminal velocities in the coma, slowly drifting away from the nucleus instead of rapidly accelerating due to gas resistance. This will create a compact comet where the dust stays close to the nucleus rather than trailing off into a tail. Furthermore, fluffy aggregates may be subject to destruction due to solar pressure or electrostatic forces, breaking down into smaller particles that scatter light less effectively, causing the tail to appear optically dim, even if it is physically present. Speculations about artificial materials are inevitable, but poorly substantiated. Could engineering dust create a strong negative polarization? Hypothetically, yes. Carbon nanotubes, graphene films, and metamaterials with specific optical properties can scatter light in unusual ways. However, the use of such materials requires an explanation of why the artificial object decided to mimic the polarization of natural dust, why it chose such scattering behavior, and what goal this imitation pursues. Speculations lack motivation and mechanism, making them entertaining but scientifically unproductive without supporting evidence. Polarimetric data contributes to a constellation of anomalies. This is another dimension that places the trio 3 and Atlas on the statistical boundary of comet behavior. Another indicator suggesting that this object is unusual even among the diverse population of comets we have studied. Is this unusualness a reflection of natural diversity, as interstellar objects form under various conditions and may systematically differ from the comets of the solar system, or is it something more exotic, remains a subject of debate. Some researchers warn against excessive interpretation of single measurements. Polarimetry is a complex task that requires careful calibration, precise knowledge of systematic errors of instruments, and corrections for atmospheric effects that can introduce false polarization. Observations of the trio 3 and Atlas were conducted at the limits of capabilities, considering the dimness of the object, and errors in polarization measurements may underestimate systematic uncertainties. Additional data with a better signal-to-noise ratio might show less extreme values, returning the trio of 3 and Atlas to normal limits, but measurement standards and numerous independent observations indicate consistent results, suggesting the reality of deep negative values rather than artifacts. If this is really the case, then it requires an explanation, either through porous dust structures, exotic compounds, or mechanisms that we have not yet fully considered. Future observations, especially using JUS with polarimetric capabilities, can refine these measurements, confirming or disproving extreme values and helping to distinguish competing interpretations. The question of dust becomes central to understanding the nature of the trio 3 and Atlas. Is this object merely a comet with unusual grain properties arising from its interstellar heritage? Or is the dust itself a clue pointing to deeper mysteries? Perhaps ancient materials from a thick disk? Perhaps organically rich aggregates containing prebiotic chemistry? Perhaps we cannot imagine what lies beyond our experience, limited to the solar system? Polarimetry hints at answers but simultaneously introduces uncertainty, adding layers to the mystery without resolving it. It's like a crossword clue that fits several words equally well, prompting a search for additional constraints before confidently filling in the blanks. The ninth part examines alternative hypotheses and exotic theories. Each anomaly allows for multiple explanations, and Atlas 3.8 has gathered enough anomalies to support an entire taxonomy of hypotheses, from the ordinary to the exotic. The scientific method requires us to exhaust natural explanations before resorting to the unusual. Let's first list standard possibilities and then cautiously move to more provocative ideas. The simplest natural explanation for the missing tail is related to the geometry of observation. If the tail is directed straight towards or away from the Earth, aligned with our line of sight, it becomes invisible due to shortening, compressing to a point instead of extending across our field of view. This explanation is geometrically plausible and does not require unusual physics, but it faces difficulties. Multiple observatories in different locations, observing for several weeks, should have provided diverse angles of view, but none of them noticed a clear extension of the tail. Geometry must be secretly aligned over several observational epochs, which casts doubt on statistical reliability. The second natural explanation is related to low dust production. If 3.8 produces gas, but the minimum amount of dust is possibly due to its composition of fine-grained materials or because the surfaces hinder dust capture, the tail will mainly consist of ions rather than dust. Ion tails are less bright, primarily visible in ultraviolet wavelengths, where ionized molecules emit light that can easily be missed in observations. This corresponds to spectroscopic data showing the presence of gas and imaging data that does not show a visible tail. But this does not fully explain why dust production is so suppressed compared to gas, especially for an object actively evaporating carbon dioxide. The third explanation emphasizes the unusual properties of dust. Large particles, high porosity, or sticky aggregates that fall back to the core instead of being carried away in the tail. We have discussed this before, but it is worth repeating that this is the most preferred hypothesis among most researchers. It does not require exotic physics, fits into the variety of observed comments, and agrees with the polarimetric data on plump particles. The absence of a tail becomes a consequence of dust dynamics rather than a lack of sublimation. The prevalence of carbon dioxide opens another aspect. The sublimation of water effectively captures dust, as the latent heat of water sublimation is high, causing vigorous gas flows that carry the dust away. The sublimation of carbon dioxide is less energetic per molecule, creating weaker gas flows that may be less effective at lifting dust. If the object Three Eyes of Atlas mainly consists of carbon dioxide with minimal water content, then dust capture can be reduced even during significant sublimation processes, leading to gaseous but dust-poor emissions. Particle absorption opens a fifth possibility. If the dust particles are unusually dark, possibly containing carbon organic matter or iron-rich silica, they will weakly scatter sunlight even if present in significant amounts. The tail will physically exist but remain optically invisible, hidden as it reflects insufficient light to stand out against the sky. This explanation faces difficulties, as observations record the presence of dust particles, indicating that the grains are not completely non-reflective. These particles may differ from tail particles in size or composition. Exotic hypotheses arise when natural explanations fail. The least exotic explanation is that the Three Eyes of Atlas is a transitional object that is neither fully a comet nor fully an asteroid, possibly a fragment of a larger body, partially processed by internal heat or collisions, leading to unusual distributions of volatile substances and dust properties. Such objects can exist in the populations of the solar system, occupying blurred boundaries between comets and asteroids where classification becomes unclear. A more provocative hypothesis is about artificial construction. If the Three Eyes of Atlas is a manufactured object, such as a probe, a derelict spacecraft, or a fragment of a solar sail, it could be emitting gas from residual volatile substances accumulated over millions of years of interstellar travel, without forming the dust tail characteristic of natural comets. The designed surface could intentionally minimize dust formation to avoid contaminating tools or reduce radar cross-section for stealth purposes. The prevalence of carbon dioxide could be the result of a conscious choice of fuel or an accidental accumulation of interstellar carbon dioxide on external surfaces. This hypothesis faces immediate objections. Where are the signs of geometric regularity? Artificial structures typically have straight lines, right angles, and modular construction, features not observed in the unresolved images of Three Eyes of the Atlas. Where are the material signatures? Metals, polymers, and composites must exhibit distinctive spectroscopic or polarimetric features different from stone and ice. However, observations show a composition that generally matches natural minerals and organic substances. Where is the anomalous dynamics? Artificial objects can demonstrate controlled changes in orientation, maneuvers using thrust, or electromagnetic radiation. None of this was detected. Loeb's hypothesis about the solar sail, initially applied to Oumuamua and now reiterated for Three Eyes of Atlas, suggests a thin, reflective surface accelerated by solar pressure. The acceleration forward noted in astrometric data may arise from radiation pressure if the object is properly oriented. The absence of a tail becomes a logical consequence. Sails do not form tails unless they are covered with volatile substances that sublimate, and even then, the formation of tails will differ from cometary norms. The detection of carbon dioxide may be linked to ice accumulated on the sail during interstellar travel, which is now sublimating under solar heating. However, the hypothesis of the light sail faces the problem of rotation. Sails under the influence of radiation pressure will experience forces that quickly spin them if they are not perfectly symmetrical or do not use active stabilization. The Three-Eyed Atlas, considering the 16-hour rotation, shows no stabilization, indicating a naturally irregular body rotating under the influence of angular momentum conservation. Moreover, the spherical symmetry of the coma contradicts what one would expect from a sail that should demonstrate asymmetric gas emission from one side heated by sunlight. Another exotic possibility is a sleeping comet undergoing a reactivation phase. Perhaps the Three-Eyed Atlas has spent millions of years in interstellar space, its surface volatiles depleted by cosmic rays, forming a crust that prevents sublimation. As one enters the inner solar system, the sun's heat gradually breaks down the crust, allowing gas to escape, but not yet actively enough to form dust. The tail may appear later when activity increases, indicating we are observing an object in a transitional state between dormancy and full activity. The angle of panspermia is also worth mentioning. If a Three-Eyed Atlas emerged in a system where life exists, could it have transported biological material, spores, dormant microbes, organic molecules synthesized by living processes? Unusual organic signatures indicated by spectroscopy may hint at biological origins, although distinguishing biotic from abiotic organic substances remotely is nearly impossible. Proponents of panspermia note that the spread of life between stars through ejected comets is thermodynamically plausible. A small portion of discarded material ultimately ends up on habitable planets, with some organisms capable of surviving in a frozen state during the journey. A three-eyed atlas becomes a potential carrier, a biological ambassador from another world. This is speculation layered upon speculation. We do not know if organic substances are unusual. We do not know if they are biotic. We have no means to test biosignatures remotely with modern tools. But this idea is intriguing because it transforms the three-eyed atlas from a mere curious find into potentially the most important scientific discovery in human history. Direct evidence of extraterrestrial life, even if it's just microbes, even if they have long been extinct, delivered to our solar system through natural processes. Parallels with pop culture are inevitable. Arthur C. Clarke's cylindrical alien artifact, Rendezvous with Rama, entering the solar system disguised as an asteroid, has captivated the imagination for decades. The myth of the Black Knight's companion, supposedly an artificial object in Earth's orbit, persists despite denials. Every unusual astronomical observation is filtered through these narratives, cultural patterns for interpreting anomalies as artificial objects. The three eyes of the atlas correspond to this mysterious, anomalous, and resistant pattern to simple explanations, making them the perfect screen for projecting our hopes, fears, and expectations inspired by science fiction. The key question permeating the speculations is why the European Space Agency treats this so urgently. Assignments, public announcements emphasizing surprise, and the rapid publication of initial results indicate that the institution has realized the three eyes of the atlas have scientific significance beyond routine comet observation. Does the European Space Agency know something that has not yet been disclosed? Have internal analyses uncovered additional anomalies not mentioned in published articles? Or is this urgency simply a rational response to a rare opportunity? Understanding that interstellar visitors do not wait for bureaucratic schedules and must be observed while available. Transparency in science implies the absence of hidden sensationalism. Major discoveries typically seep through conferences, preliminary publications, and informal discussions before official release. If the European Space Agency discovered clear evidence of artificial origins, geometric structures, radio signals, or impossible materials, someone would have already talked about it, and rumors on the internet would spread faster than official messages. The absence of such rumors suggests that there are no clear clues, only accumulating oddities that collectively demand attention but prove nothing definitive. The epistemological task is to recognize the moment when anomalies cease to be noise and begin to be a signal. One anomaly is curiosity. Two may be coincidence. Three raise questions, but four or five in one object start to resemble a pattern. The three eyes of the atlas gathered a collection: the absence of a tail, the predominance of carbon dioxide, unusual polarization, acceleration forward, and the tilt of red dust, which individually may have natural explanations, but together cause anxiety. At what point does the unusual yet natural become something else? We must seriously consider alternatives. Science has no fixed threshold, only a cultural tendency towards conservatism that resists exotic explanations until the data compels it. However, such pressure has not yet occurred with the three eyes of the atlas and may never happen. Future observations may clarify everything naturally, showing the formation of a tail at perihelion, confirming the properties of particles, explaining polarization, demonstrating that carbon-rich comets from a thick disk simply behave differently than we expected. The riddle will disappear, giving way to a deeper understanding of the diversity of comets and the properties of interstellar objects. Science will develop gradually, adding another data point to the catalog, another lesson about the ingenuity of nature. Or anomalies may continue to exist, stubbornly resisting natural explanations, demanding an expansion of our understanding of cosmic debris to include possibilities we have barely considered. Such an expansion does not necessarily indicate the presence of aliens. It may point to new physical processes of dust aggregation, unexpected chemical reactions in ancient stellar conditions, or dynamics that we have not modeled because we have never encountered the appropriate conditions. However, this would mean acknowledging that our current models, based on the experience of the solar system, may be incomplete or even misleading when it comes to objects from beyond. And in this recognition lies the true value of interstellar visitors, not as potential artifacts, but as teachers, forcing us to confront the limitations of our knowledge and expand our understanding to encompass the diversity of a wider galaxy. The question is not whether a three-dimensional atlas is natural or artificial. The question is whether we are intellectually flexible enough to recognize new categories of the natural as they emerge, or if we will remain trapped in false dichotomies that limit rather than liberate our thinking. Part 10. Hidden corners, tensions, and anxious signs. Science rarely moves smoothly from observation to understanding. More often, the path twists through contradictions, ambiguous measurements, and debates where rational people interpret the same data differently. The three-dimensional atlas embodies this convoluted reality, presenting a complex set of dimensions that refuse to coalesce into a simple narrative. Let's examine the specific tensions that make this object both irritating and fascinating. Firstly, the issue of brightness. Initial estimates based on visible size and distance suggested that the core of the three-dimensional atlas could reach several kilometers in diameter, sufficient for significant gravitational influence to retain substantial volumes of volatile substances. However, the image from ExoMars showed an unresolved core, which may mean it is much smaller than these estimates, possibly just a few hundred meters in diameter. How can we reconcile a brighter visible magnitude with a potentially small size? Either the albedo is significantly higher than that of typical comets, reflecting more sunlight per unit area, or the coma contributes more to the overall brightness than expected, or our initial size estimates were simply wrong due to unreliable assumptions about dust scattering efficiency. This matters because size determines mass. Mass determines gravitational connection, and connection determines whether the exhaust can significantly change the trajectory of an object. Small objects experience stronger accelerations at the same exhaust speeds compared to larger objects. If the three-dimensional atlas is small, then the non-gravitational accelerations mentioned by Loeb become easier to explain naturally. If it is large, then these accelerations require more intense or asymmetric exhaust to achieve observable changes in trajectory. Secondly, there is tension in the very dimensions of acceleration. Different researchers analyzing the same astrometric data come to different conclusions about the magnitude and direction of non-gravitational forces. Some find directed acceleration corresponding to Loeb's claims. Some researchers discover accelerations perpendicular to the line connecting an object to the sun, which corresponds to typical comet behavior. Others claim that the uncertainty of measurements is significant enough that any statements about detections are at best questionable, possibly being artifacts of systematic errors in positional measurements or in star catalogs. This is not uncommon in the astrometry of asteroids and comets. Measuring small accelerations requires high precision and minimal systematic errors. Atmospheric refraction, inaccuracies in telescope tracking, and discrepancies in catalogs can disguise themselves as real forces. The debates will only be resolved through additional observations covering longer time intervals, allowing for the integration of trajectories, averaging random errors, and revealing true dynamic behavior. But while uncertainty reigns, statements about unusual accelerations remain contentious. The third unresolved question about the core creates the main uncertainty. We do not know the shape, surface properties, orientation of the axis of rotation, or detailed composition of the core. Everything we see is a coma, that blurred shell which may hide numerous nuclear configurations. Is the core elongated like Oumuamua, or roughly spherical? Is it a single piece or a loose clump held together by weak gravity? Does it have surface features, craters, cliffs, jets? Or is it smooth and devoid of details? These uncertainties permeate every analysis, forcing researchers to make assumptions that may turn out to be completely wrong. Technical complexities exacerbate these uncertainties. The 3I Atlas object is weak, requiring long exposures that accumulate noise and complicate background subtraction. It moves, necessitating tracking that can introduce blur or require complex image overlays. It is distant, and better tools are needed to resolve the details, working at the limit of their capabilities. Even Hubble and James Webb face difficulties when working with such faint and rapidly moving objects. creating images and spectra with a signal-to-noise ratio barely exceeding the detection threshold. It is also worth considering the bias of choice. Recent history leads us to search for anomalies in interstellar objects. The strangeness of Oumuamua set expectations that subsequent visitors would also be unusual. Every deviation from typical comet behavior is highlighted, discussed, and becomes a subject of debate, while familiar behaviors are noted but quickly forgotten. This does not mean that anomalies are illusory. They are real dimensions, but it may mean that we interpret them through the lens of expectations, which enhances their significance beyond what is supported by data alone. Red flags accumulate when several independent anomalies appear in the same object. Each of them can be explained separately. The predominance of carbon dioxide, interstellar origin, absence of a tail, geometry or grain size, unusual polarization, porous dust, forward acceleration, asymmetric ejection. But explaining all these factors simultaneously so that they mutually agree becomes much more difficult. A model is needed where carbon dioxide predominates, producing gas flows that inefficiently lift dust, creating porous grains through special aggregation processes that align with emission patterns, ensuring linear acceleration. Every step seems plausible, but collectively the scenario begins to appear increasingly fabricated. Bayesian thinking comes to the rescue, where probabilities are updated based on accumulated data. One anomalous case slightly increases the likelihood of exotic explanations, but insignificantly. However, if there are many anomalies, each one shifts the probabilities further. At some point, although the exact boundary is subjective, the accumulated weight of evidence makes exotic explanations competitive with traditional ones. Not because any single dimension confirms an exotic case, but because traditional explanations become too strained, trying to account for everything at once. Critics argue that this is where Bayes' influence manifests. If a low probability of artificial origin is initially set, which most scientists do considering the rarity of technological civilizations in the universe, then even many anomalies do not significantly change this probability. You still lean towards natural explanations, as the initial probability strongly supports them. Only by starting with higher probability values for artificial or exotic natural processes will anomalies significantly shift your posterior probabilities towards these alternatives. The tension between public and scientific opinion exacerbates these debates. Headlines report on a comet resembling an alien or a mysterious object that baffles astronomers, creating an impression of consensus amidst confusion, while an active discussion is underway within normal scientific practice. Scientists reading such headlines feel awkward, watching their cautious qualifications and uncertainties turn into sensationalism. However, the audience, craving cosmic significance and disappointed by years of rumors about possible aliens, clings to anomalies as hints that this time we have truly found something strange. Yes, a response based on caution but engagement follows the golden mean. The agency acknowledges the surprise that caught everyone off guard while not supporting exotic explanations. It reallocates the JUICE project, emphasizing its scientific importance without claiming any breakthroughs. Data and images are published quickly, maintaining transparency without premature conclusions. This professionalism inspires confidence, but also disappoints those seeking clear answers. Is the triadic object atlas strange, or simply unusual? Is this commotion worth it, or are we overreacting to the noises of measurements and the effects of choice? More questions arise as observations continue. Will history emerge after perihelion, when solar heating reaches its peak? Will JUICE solve the mystery of the core, or provide better coma characteristics? Will spectroscopy reveal additional chemical surprises, perhaps isotopic ratios indicating ancient stellar environments, or molecules unknown in the comets of the solar system? Will polar images clarify the properties of dust, narrowing the range of compositions and structures corresponding to observations? Will long-term astrometry resolve the dispute over acceleration? Can we distinguish real forces from measurement artifacts? Each of these questions may resolve in such a way that the third atlas returns to familiar categories, possibly with a few notes on its unusual yet explainable properties, or they may deepen the mystery, confirming anomalies and adding new ones, distancing the object from conventional explanations. Science thrives in this uncertainty, in the productive tension between data and models, observations and theories. However, society, even some scientists, crave resolution, the satisfaction of understanding comfortable categories that fit. What we observe is science in its rawest form, chaotic, uncertain, controversial, honest in its ignorance. This is much more useful than false confidence, more authentic than premature consensus, but it is uncomfortable, leaving us in a suspended state between possibilities, preventing any hypothesis from being declared victorious. The third atlas teaches patience, humility in the face of complexity, and respect for the difficulties of extracting truth from fragmented, noisy, ambiguous data collected over millions of kilometers of space. Red flags do not signal danger, but serve as markers of border territories, areas where our maps are incomplete and understanding is temporary. Exploring this territory requires courage to speculate, balanced with the discipline to demand evidence, imagination to consider exotic possibilities, tempered with skepticism that prevents desire from masquerading as discovery. Part 11. The Story of Origin. A thick disk, an ancient interstellar home. Each object carries the history of its birth, encoded in its chemistry, structure, and dynamics. For the third atlas, this story begins not in our cosmic neighborhood, but in the ancient expanses of the thick disk of the Milky Way. The population of stars formed when the galaxy was young and the universe was less saturated with heavy elements. Recent work on orbital modeling, integrating the trajectory of the third atlas back through millions of years of galactic dynamics, suggests this unexpected origin, not from the thin disk where our sun resides, but from the expanded halo of old stars swirling above and below the galactic plane. A thick disk formed 8 to 12 billion years ago, in an era when the Milky Way was smaller, more chaotic, and chemically different from today. The stars in the thick disk show low metallicity, with fewer heavy elements like carbon, oxygen, silicon, and iron, as the interstellar medium from which they condensed was not enriched by many supernovae. These stars rotate around the galactic center at higher speeds perpendicular to the plane of the disk, slightly tilted and eccentric, reflecting the violent processes that shape the thick disk. Perhaps the reason for this is the merging of galaxies or intense star formation in the turbulent early times of the galaxy. If the object 3 in Atlas arose in a planetary system around a star of a thick disk structure, its chemical composition becomes clearer. In environments with a low metal content, various sequences of mineral condensation form in protoplanetary disks. The ratio of carbon to oxygen changes, affecting how carbon bonds in carbon monoxide, carbon dioxide, or organic molecules compared to how it can bond in silicates or graphite. The abundance of water ice may be lower if oxygen is insufficient or primarily bound in other forms. The dominance of carbon dioxide that we observe may be direct evidence of formation in an environment with low metal content and high carbon content, unlike the metal-rich nebula from which the solar system formed. The reverse integration of the trajectory, necessary to determine the origin of the 3 in Atlas, requires significant computational resources and involves many uncertainties. It all begins with his current position and speed, measured by astrometric observations, and the equations of motion are integrated back in time, taking into account the gravitational forces from the sun, planets, nearby stars, the galactic disk, the core, dark matter, and other significant masses that could disrupt the trajectory. For millions of years, small uncertainties in initial conditions and gravitational potential accumulate, creating a cloud of probabilities rather than a single, clear trajectory. This cloud expands as we move into the past, ultimately encompassing many possible regions of origin. Despite uncertainties, modeling consistently points to a thick disk rather than a thin disk or populations of a galactic halo. The current velocity vector of the object, its orbital tilt relative to the galactic plane, and its energy all indicate an origin from a thick disk. This does not allow for precise identification of a specific star system. Too much time has passed, too many dynamic interactions have occurred, but this narrows the possibilities down to stars of a certain age, metal content, and kinematic families. This result elevates 3 and Atlas from the level of interesting to the level of valuable. Objects from the thick disk are rare visitors to the inner solar system. Most interstellar objects likely originate from thin disk stars, like our Sun, young systems with a metallic composition similar to ours. Thick disk objects open a window into the history of the galaxy, revealing the chemical conditions that existed billions of years ago, before the Sun formed amidst the variety of planetary systems that arose when the galaxy was fundamentally different from today. Could this explain the unusual composition? Almost certainly, at least in part. Comets forming around stars with low metal content will include various mixtures of ice, different dust compositions, and various organic reserves compared to the comets of the solar system. The dominance of carbon dioxide, the tilt of red dust, and possibly even unusual polarization may reflect the chemical conditions of formation, determined by the elemental abundances of surrounding stars. Laboratory studies of meteorites from metallic and porous environments, if we had them, which we do not, could show similar deviations from the norms of the solar system. There is also the question of age. If Atlas III's is between 8 and 12 billion years old and formed shortly after the parent star, then it has wandered the galaxy for entire epochs, significantly surpassing the age of our solar system, which is 4.5 billion years. For this vast amount of time, the object has been bombarded by cosmic rays, exposed to ultraviolet radiation from passing stars, struck by interstellar dust, and subjected to thermal cycles in changing radiation fields. These processes alter the chemical composition of the surface, creating organic residues, amorphizing crystalline structures, and causing the loss of volatile substances from the outer layers. An ancient object may behave differently than a young one. Volatile substances can be depleted from the surface layers, forming crusts that hinder sublimation until sunlight breaks through them. Dust particles can be further processed, their structure altered by radiation damage, and their surfaces coated with an organic resinous substance formed as a result of photochemical reactions. Unusual polarization may partially reflect billions of years of erosion that no comet in the solar system has experienced, simply because solar system objects are much younger. Speculations about ancient probes inevitably arise when discussing the origin of thick disks. If technological civilizations exist, some may have arisen in the thick disks of ancient stellar populations, possibly billions of years before the formation of Earth. A civilization 8 billion years old would have had time to spread across the galaxy, sending probes to countless systems, perhaps even going extinct, leaving only its artifacts wandering in space. The Atlas of Three Eyes, if it were such an artifact, would become an abandoned relic, its systems long dead, its mission forgotten, and its creators vanished. We would study archaeological material from a civilization older than our planet. This is a deep speculation, unsupported by evidence, but it illustrates how origin stories change context. An object made of a thick disk holds significance beyond its physical properties. It is a time traveler, an envoy from a distant past, potentially a specimen of conditions and processes we cannot explore anywhere else. Even if it is completely natural, its scientific value is invaluable, and all efforts should be made to characterize it, as the information contained within cannot be obtained by any other means than interstellar travel to the stars of the thick disk directly. The historical context from panspermia theories adds another dimension. If life arose in the early stages of galactic history, possibly aided by older, metal-poor stars with suitable planets, then comets and asteroids ejected from these ancient systems could have seeded younger systems with organic molecules, amino acids, and perhaps even viable microorganisms. Panspermia does not require intentional seeding. Natural ejection processes are quite sufficient. However, if a triple atlas of eyes emerged from a thick disk system that could support life, it may contain chemical or biological signatures indicating the existence of extraterrestrial biology, its distribution, and antiquity. Detecting such signatures remotely using modern technology is practically impossible. We will need samples that can be analyzed in laboratories on Earth using methods sensitive enough to distinguish between biological and abiotic organic materials, sterile and contaminated substances, ancient and recent deposits. But such a possibility lures, turning a triple atlas of eyes from cosmic debris into a potential key to astrobiology. This opens the way to understanding whether life is widespread in the galaxy, whether it spreads between stars, if we are alone, or part of a much larger biological community. The origin from a thick disk also implies that interstellar objects are more diverse than our small sample suggests. If visitors come from different stellar populations, the thin disk, the thick disk, the halo, possibly even extragalactic objects from satellite dwarf galaxies merging with the Milky Way, each experiences different formation conditions, chemical abundances, and evolutionary histories. Oumuamua, Twai Borisov, and the triple atlas of eyes may represent different categories rather than variations of a single theme. Characterizing this diversity requires much more discovery, better statistics, and a deeper understanding of how galactic dynamics bring objects from different populations into the inner solar system. Looking to the future, the hypothesis of origin from a thick disk makes testable predictions. If so, the isotopic ratios of the triple atlas of eyes should differ from those of the solar system, showing signatures of nuclear synthesis in low-metal stars. His organic molecules, if identified, may have unusual compositions reflecting various synthetic pathways. The mineralogy of his dust may include phases rare for materials in the solar system, but expected during condensation with low metal content. Each of these predictions can be verified using enhanced spectroscopy, polarimetry, and in the future, if we're lucky and ambitious, through sample return missions that intercept interstellar objects and bring physical materials for laboratory study. This future remains distant but conceivable. Technologies are advancing, exploration capabilities are improving, and interest in interstellar objects is growing. For several decades, we can regularly discover dozens of visitors each year, characterize them in detail, and possibly even send spacecraft for rapid response to particularly interesting targets. In this context, the triple atlas of eyes becomes a pioneer, an object that made us seriously contemplate galactic origins, ancient chemistry, and the possibility that each interstellar visitor is unique, carrying stories from corners of the galaxy we will never visit but can study through the messengers that occasionally cross our path. Part 12. A triple atlas of eyes amidst interstellar visitors. After 8 years of intensive searches, the existence of 3 interstellar objects has been confirmed. This establishes a certain detection rate, but does not yet allow for determining their overall population. Each of these visitors is significantly different from the previous ones, indicating the vast diversity of interstellar space, or that our selection is too small to reveal hidden patterns. Let's compare 3 objects with their predecessors to understand what they add to our emerging picture of wandering debris in the galaxy. The first of these was Oumuamua, discovered on October 19, 2017, by the Pan-STARRS telescope in Hawaii. Its name, meaning scout or messenger in Hawaiian, turned out to be very fitting. It was indeed the first confirmed interstellar visitor, although retrospective searches found no images prior to its discovery, despite having passed through well-studied areas of the sky. The most noticeable feature of Oumuamua was its extreme elongation, inferred from changes in brightness, suggesting an axis ratio of about 10:1, resembling a cigar or possibly pancakes, depending on assumptions about its rotation. He had no visible coma or tail, despite being within 0.25 astronomical units from the Sun, significantly closer than Mercury's orbit, where any ice should have intensely vaporized. Nevertheless, Oumuamua exhibited non-gravitational acceleration away from the Sun, indicating some form of gas emission despite the lack of a visible coma. This paradox sparked heated debates. Natural explanations referred to hydrogen ice, nitrogen icebergs, or very weak sublimation producing gas but no dust. Exotic theories supported by Loeb suggest artificial origin, possibly a solar sail propelled by solar radiation pressure. The debates remain unresolved, and most astronomers lean towards natural explanations, while acknowledging that Oumuamua is indeed a strange object. The second interstellar cometary object was Borisov, discovered in August 2019 by amateur astronomer Gennady Borisov. He behaved more predictably. He had a clear coma and tail. Spectroscopy revealed the presence of water vapor, carbon monoxide, and typical cometary volatiles. Its composition had a high level of carbon monoxide, indicating formation in the cold outer regions of the parent system, but nothing obviously anomalous was observed. Polar images showed normal values. The dust ejection speed matched expectations, and the non-gravitational forces aligned with typical comet gas release models. Borisov became the interstellar comet everyone expected, confirming that not all visitors are strange and that familiar physics also works in other star systems. Now the third object appears on the scene, Atlas, which has a hybrid nature. It is more active than Oumuamua, but less impressive than Borisov, occupying an awkward middle ground. It has a coma that confirms activity, but no visible tail, indicating suppressed dust production. Its composition is unusual but not impossible. Carbon dioxide predominates in ratios atypical for solar system comets, but can be explained by interstellar heritage. Its polarization is extreme, yet within natural values, considering the unusual dust structures. Its dynamics demonstrate possible non-gravitational forces, although measurements remain contentious. What patterns can be highlighted when comparing these three objects? First, diversity truly exists. Visitors from interstellar space do not fit into a single model. They vary in size, shape, composition, activity level, and behavior, just as comets and asteroids in the solar system vary significantly despite common origins. This indicates that the processes of planet formation and ejection operate similarly throughout the galaxy, but with sufficient variation in parameters such as star mass, metallicity, disk temperature profiles, and configurations of giant planets, leading to a wide range of outcomes. Secondly, anomalies can be commonplace. 2 out of 3 interstellar guests displayed such behavior that it sparked scientific debates. Oumuamua, with its acceleration and lack of a tail, three-eyed Atlas with its tailless activity and unusual composition. If this ratio is correct, then most interstellar objects will somehow challenge expectations, either because they truly differ from their counterparts in the solar system, or because our detection bias tends towards unusual objects that appear bright or behave strangely, making them easier to notice and study. Third, our understanding remains preliminary. Each new visit forces us to revisit theoretical approaches, adjust models, question assumptions, and introduce new mechanisms. This is healthy scientific progress, indicating that the field of science is alive and responsive to data, rather than rigid in dogmas. However, it also shows how little we actually know about the populations of interstellar objects. Are they more like Borisov with Oumuamua and the three-eyed Atlas as exceptions? Or conversely, is Borisov the exception while the oddities are typical? We cannot answer this question with only 3 data points. Improvements in detection promise rapid sample expansion. The Vera Rubin Observatory, when fully operational, will be able to detect dozens and hundreds of interstellar objects each year, creating statistical samples large enough to reveal true patterns as opposed to random variations. For a decade, we will learn whether the prevalence of carbon dioxide is common among interstellar comets from certain environments, if most objects exhibit weak tails, and whether non-gravitational forces typically align with solar heating or indicate other processes. Uncertainty will diminish, giving way to knowledge based on reliable statistics. Speculative possibilities remain around the idea of man-made objects. Even if a tiny fraction of interstellar objects turns out to be artificial, ejected by probes, fragments of solar sails, or technological debris, the increased rates of their detection may reveal them through statistical anomalies. Certain size ranges may be suspiciously overpopulated. Trajectories might show non-random clustering near the ecliptic or planetary orbits. Spectroscopic signatures may indicate materials that cannot be formed naturally. These signals will be subtle and require large samples for detection, but if found, they will be decisive. Otherwise, all objects may be natural, and apparent anomalies arise from observational biases, measurement limitations, and insufficient theoretical models. We can look back 20 years from now and laugh at how primitive our understanding was in 2025, how we confused ignorance with mysticism, how we made assumptions about aliens when we simply failed to understand the physics of porous dust aggregates in low-metal objects. This modesty is important. Science advances by recognizing its limitations rather than clinging to mysteries when explanations arise. The comparison also highlights what we lack. We have images but lack detailed photographs. We have spectra but no mass spectrometric data of real samples. We possess dynamics but have no direct measurements of emissions or surface properties. Every interstellar guest was studied from millions of kilometers away, observed through telescopes operating at the edge of their capabilities, and characterized through indirect conclusions rather than direct verification. The next revolution in the science of interstellar objects will occur due to proximity. Spacecraft launched to intercept these visitors, possibly even missions to return samples that will bring materials back to Earth for laboratory analysis. Such missions face enormous technical challenges. Interstellar objects move quickly and are detected late, leaving little time to launch interception trajectories. They are far away at the moment of discovery, requiring several years for travel, even if we launch immediately. Their sizes and dangers are unpredictable. Approaching a comet actively emitting gas can damage a spacecraft due to dust impacts or gas jets. However, the scientific results will be transformative, turning vague remote sensing data into concrete physical and chemical data that will ultimately resolve current disputes. At present, 3 interstellar objects are included in the catalog, and 3i Atlas has become the third confirmed member, a strange but possibly not anomalous representative of the wandering population of the galaxy. He shows us that interstellar space is filled with remnants of planet formation throughout the history of the galaxy, that these objects reflect chemical and physical conditions we cannot access in any other way, and that each visitor is a gift. Free samples delivered to our door, requiring only our attention and study before disappearing back into the darkness from which they came. Is the 3i Atlas the most interesting of the 3 or just the latest? Time and further observations will tell. But his place in the sequence is secured, a step in the gradual expansion of humanity's awareness from our solar system to a broader galactic community of wandering objects that connect all stars through a slow exchange of debris over light years and eons. Part 13. Other recent headlines in astronomy. The universe refuses to conform to our attachment to narrow themes. While 3i Atlas draws attention, other astronomical discoveries unfold, each altering our understanding of the cosmos, life, and humanity's place within it. Let's briefly consider the broader context of recent months, noting how these parallel stories enhance or illuminate themes arising from our interstellar visitor. At the end of September 2025, the James Webb Telescope published spectroscopic observations of the exoplanet K2-18b, a mini-Neptune orbiting a red dwarf star 120 light-years away from us. Spectra revealed the presence of methane and carbon dioxide in the planet's atmosphere, which is expected for a hydrogen-rich world, but also hints of dimethyl sulfide, a molecule produced almost exclusively by biological processes on Earth, especially by marine phytoplankton. This discovery remains preliminary and requires confirmation through additional observations, but if confirmed, it will be the first potential biosignature found on an exoplanet, turning the search for life from a theoretical exercise into a concrete observation. The parallels with the Project 3, I Atlas, are subtle but real. Both stories are connected to the interpretation of ambiguous data, distinguishing true signals from noise and systematic effects, as well as the necessity to report preliminary results before achieving final certainty. The detection of dimethyl sulfide may turn out to be an artifact, contamination, or misinterpretation, just as the anomalies of the 3 Atlas may be measurement errors or incomplete models. However, both topics attracted attention, as the potential consequences, life on another planet, artificial objects in our solar system, are serious enough to warrant close scrutiny, even when the probabilities remain low. In early October, a powerful coronal mass ejection from the Sun narrowly missed Earth, passing through the orbital space that Earth occupied just a few hours earlier. The solar storm was classified as level X5, powerful enough to disrupt satellites, damage electrical grids, and create a bright glow visible at mid-latitudes. The Earth's miss was a result of luck, not prediction, reminding us that cosmic dangers appear unexpectedly, and our monitoring capabilities, though improved, are still far from perfect. Forecasting solar activity is a complex task, and predicting the exact trajectories of ejected plasma is even more difficult. This is related to the Tri-Alpha Atlas project through the theme of cosmic surprise. We envision astronomy as a predictive, controlled science where equations provide precise forecasts, but reality is much more complex. Solar eruptions become surprises, interstellar visitors appear suddenly, and our models constantly need revisions when data contradict expectations. The universe is not obliged to behave predictably, and humility before its complexity serves better than confidence in incomplete models. Another important piece of news was the discoveries made by the Jupiter Space Telescope, launched in 2023 to map dark matter and dark energy billions of light years away. Early data showed the distribution of galaxies, revealing unexpected large-scale structures, voids, and filaments that were more pronounced than simulations predicted. This may mean that our cosmological models need adjustments, or that observations reveal details overlooked in previous studies. The debates continue, and theorists rush to explain or refute anomalies, depending on their views on how well we understand the fundamental structure of the universe. Parallels with the 3i Atlas are a recurring theme. Astronomy repeatedly encounters data that doesn't quite fit within existing frameworks. Observations that challenge existing models, measurements that make us question whether anomalies are true signals requiring new physics, or artifacts needing better understanding of systematic issues. This field of science advances through such tension, balancing between openness that allows discoveries and skepticism that prevents false claims from derailing progress. These headings also serve an educational purpose, reminding us that oddities are commonplace in astronomy. Every week, unexpected discoveries emerge. Black holes behave unpredictably, galaxies are found in unexpected places, star explosions do not match models, and exoplanets possess exotic properties. The fact that the Tri-Eye Atlas is unusual does not make it uniquely problematic. The unusual is the basic state of astronomy. What changes is the need for better data, better theories, or, very rarely, radically new paradigms. Public perception mixes these categories, viewing each headline as a potential paradigm shift. Scientific communicators struggle to navigate this confusion, trying to convey to people that most anomalies are resolved through familiar corrections, improved calibrations, refined models, and additional observations that fill the gaps, while not suppressing the legitimate excitement when rare paradigm shifts actually occur. If the biosignature of the exoplanet is confirmed, it will be a paradigm shift. The structures discovered by the Euclid satellite will likely clarify rather than refute cosmology. The Atlas of 3I is located somewhere in the middle, potentially transforming if its anomalies resist natural explanation, and more interesting if they resolve in a conventional manner. It is also worth considering how discoveries interact with each other. If dimethyl sulfide turns out to be real on exoplanet K2-18b, does this increase or decrease the likelihood that the Atlas of 3 Eyes is artificial? Some argue that the probability increases. If life is common enough to detect biosignatures on nearby exoplanets, then technological civilizations may be correspondingly widespread, making artificial interstellar objects more plausible. Others believe that the probability decreases, as if life is widespread, natural organic molecules are ubiquitous, and the discovery of organic material on the Atlas of Tri-Eye does not indicate artificiality. Both arguments are speculative and poorly supported by data. We do not know if biosignatures correlate with technological development, how often intelligent species create interstellar probes, or if detectable artifacts exist in sufficient quantity to encounter them by chance. The arguments are too vague to allow for confident conclusions. They are more of an intellectual exercise than a scientific conclusion. These parallel headings create context. They remind us that astronomy in the year 2025 is incredibly active, with several fronts developing simultaneously. The James Webb Space Telescope is revolutionizing the study of exoplanets and the early universe. Solar observatories reveal complex magneto-hydrodynamic processes in star activity. Cosmological studies chart the large-scale structure of the universe with unprecedented accuracy. Gravitational wave detectors record black hole collisions every week. Neutrino telescopes investigate stellar cores and supernovae, and among all this research, interstellar objects become a new subdiscipline, connecting dynamic astronomy with planetary science, galactic archaeology, and astrobiology. The diversity of this area requires patience and perspective. 3 atlases of the eye are one piece of the puzzle in a vast jigsaw where most elements are still unfound, let alone in their places. Demanding immediate answers or final conclusions is unrealistic. Science develops gradually. Each observation imposes limitations, each measurement narrows possibilities, and each discussion clarifies hypotheses. This process frustrates those who crave quick solutions, but it is resilient and self-correcting, where hasty agreements cannot be. And perhaps most importantly, parallel discoveries show that the universe is infinitely fascinating, whether specific anomalies turn out to be mundane or revolutionary. Regardless of whether the 3-eyed atlases are natural comets or artificial probes, whether there is life on K18b or just complex chemistry, whether Euclidean structures require new physics or just better simulations, the universe remains a source of wonder, mystery, and intellectual challenge that justifies our attention and efforts, no matter how individual questions are resolved. We study not because we expect every observation to overturn physics, but because we are curious, because understanding brings satisfaction, and because sometimes, very rarely, we actually stumble upon something truly new that changes our perception of reality. Meanwhile, work continues, data accumulates, and mysteries like 3-eye atlases keep us in suspense, provoking discontent and endless curiosity about what lies beyond our current knowledge. Part 14. Synthesis. What seems to us speaks three ocular atlases. We have gone through observations, anomalies, hypotheses, and context. Now comes the challenging work of synthesis, uniting disparate parts into a coherent picture, acknowledging what we know, recognizing what we do not know, and determining what is most significant as the story of the three ocular atlases continues to unfold. Here, science reveals its true nature, not through definitive answers, but through an honest assessment of evidence, uncertainty, and next steps. The image of XMR, which we started with, remains a symbol. The object shown does not match what textbooks predicted. He has no visible tail, despite the active comet, and there is no elongation, although dust was expected to form. It is just a compact cloud that could pass for a distant galaxy, if not for its movement against the stars. This visual discrepancy sets the tone for everything that follows. Atlas's three eyes systematically defy expectations while remaining within the bounds of natural possibility. Spectroscopic data showed that carbon dioxide predominates 8 times over water vapor, overturning the typical ratio for comets and suggesting either unusual formation conditions. Perhaps this is related to the origin from a thick disk, or the chemistry of metal-poor protoplanets, or the preferential loss of volatile substances over millions of years as they wandered through star space. Both explanations are natural and plausible, but they push Atlas's three eyes to the statistical edges of comet populations, marking him as unusual even among the already rare interstellar visitors. Polar images showed extreme negative deviations reaching -2.7%, significantly deeper than typical comets, suggesting either highly porous dust aggregates, exotic particle compositions, or surface coatings altering scattering properties. In combination with red-inclined reflective spectra, suggesting carbonaceous or organically rich dust, these optical properties paint a picture of a material that does not quite match analogs in the solar system. Again, it's not impossible, but unusual. The light curve of rotation showed a period of 16 hours with moderate amplitude, indicating an elongated but not extreme core shape, consistent with natural rotation preserving angular momentum. The very act of rotation instills confidence, behaving like natural objects that spin under the relentless laws of physics, without signs of active stabilization or controlled positional changes that could indicate artificial systems. Dynamic measurements remain controversial. Some analyses show forward non-gravitational acceleration consistent with claims about lobes, others find perpendicular forces corresponding to standard cometary jets, while a third argues that measurement uncertainties are too great for a confident determination. This ambiguity reflects the difficulties of precise astrometry on faint, fast-moving objects and will only be resolved through extended observations providing longer time series. The modeling of origins, indicating ancestors from a thick disk, gives deep context. If the three eyes of Atlas really formed 8 to 12 billion years ago around metal-poor stars in the thick disk of the galaxy, it carries chemical traces from an era when the universe was younger, stars were different, and planetary systems formed under conditions unlike our solar system with its relatively metal-rich environment. This makes each anomaly more understandable, not as a violation of the laws of nature, but as an expression of natural diversity arising from conditions of formation that we have never encountered before. Unusual chemistry presents a puzzle requiring exotic solutions. This is a window into ancient galactic conditions that we have been fortunate to study thanks to this wandering envoy from a distant past. Synthesizing these elements into a coherent narrative requires acknowledgement of multiple viable interpretations. The conservative synthesis appears as follows. The three-eyed Atlas is a natural comet from a thick disk, ejected from its parent system millions or billions of years ago. It carries composite characteristics reflecting a chemistry of formation with low metal content, while the properties of the dust are altered by prolonged exposure to cosmic rays and ultraviolet radiation during interstellar transit. The formation of a weak tail is explained by the large size of particles or cohesive aggregates, while a poor viewing geometry reduces or obscures the tail that actually exists. Activity levels are moderate, corresponding to an aged, processed surface that sublimates weakly compared to the new comets of the solar system. This explanation does not require new physical theories, relying only on processes we have observed or theorized in other cases, and considers the three-eyed Atlas as an unusual but natural phenomenon, a statistical outlier within acceptable parametric space, rather than a fundamental challenge to our understanding. Most astronomers support this synthesis, considering it simple and scientifically justified. Anomalies do not disappear in this account, but they are contextualized as expected variations in a diverse population that we are just beginning to adequately study. The provocative synthesis acknowledges the same observations but views them from a different angle. It notes that multiple independent anomalies, composition, polarization, absence of a tail, possible frontal acceleration, all manifest in a single object, creating a pattern that raises doubts about randomness, even if each individual feature can be explained naturally. It is emphasized that ISA's urgent response, including the reassignment of tasks, implies institutional recognition that something in the 3I atlas requires special attention beyond the routine characterization of interstellar objects. This leaves room for possibilities that we have not yet fully explored, perhaps new physical properties of dust, perhaps exotic chemical pathways, or maybe, although this remains deeply speculative, technological origins. This synthesis does not claim that there is evidence of something exotic, but emphasizes that premature closure of the issue, declaring the mystery solved before key observations are complete, risks missing genuine discoveries if the three-eyed atlas truly represents something beyond current understanding. He advocates for continued thorough study, additional observations, and intellectual openness to interpretations that may initially seem unlikely, but become more plausible as evidence accumulates. Between these poles lies a pragmatic synthesis. We do not yet know. The data is ambiguous, the observations are incomplete, and patience is necessary until upcoming events provide additional constraints. Observations can reveal the formation of a tail as the geometry of view changes, and observations at perihelion may demonstrate a surge of activity that clarifies the mechanisms of dust formation. Long-term astrometry can clearly characterize non-gravitational forces. The continuation of spectroscopy may reveal additional molecular species that provide information about the formation environment or processing history. Each of these observations can significantly alter the interpretation. The appearance of a visible tail in the data would resolve the central visual anomaly, suggesting that observations by ExoMars simply captured the 3I atlas at an unfortunate angle or during a period of minimal activity. Spectra at perihelion, showing isotopic ratios corresponding to ancient stellar environments with low metallicity, would confirm the origin from a thick disk and explain the peculiarities of composition. On the contrary, the constant absence of a tail, despite maximum solar radiation, would deepen the mystery, prompting the search for more creative explanations as to why the gas-emitting object does not produce a visible tail. The forecast for the coming months is simple. A greater amount of data will clarify some questions while raising new ones. This is a typical trajectory of astronomy. Observations answer specific questions, but reveal unexpected complexities that require further study. The 3I atlas will not suddenly become simple and fully understandable. Most likely, our picture will become both more detailed and more complex, with some anomalies resolving naturally, while others remain or transform into new mysteries. Ground observatories will continue observations for achieving symmetry and spectroscopy, while the 3I atlas moves in its orbit. The object will shine brighter as it approaches perihelion, improving the signal-to-noise ratio and allowing measurements that are currently impossible at its weak brightness. Spectroscopists will search for isotopic signatures, the ratio of carbon-11 to carbon-12, levels of oxygen-18, and ratios of deuterium to hydrogen that reveal stories of nucleosynthesis and formation temperatures. These relationships are extremely informative, encoding information about the metallicity of parent stars, temperature gradients of dissociation, and chemical processing, which unequivocally identifies formation environments. The key to understanding the 3I atlas lies in realizing that we are witnesses to science in real time, with all its uncertainties, debates, and gradual refinements. There is no conspiracy of silence, hidden data proving the existence of aliens, or secret knowledge kept from the public. What you see are contested dimensions, conflicting interpretations, a candid acknowledgement of uncertainty. This is the true scientific process. It is complicated because reality is complex, uncertain because dimensions are difficult, and discussions arise as reasonable people interpret ambiguous data differently based on their assumptions and experiences. This transparency is valuable, even when it causes frustration. The scientific approach is not just a set of facts, but a method that allows one to approach the truth through systematic observations, careful argumentation, and collective discussions. Atlas 3. I serves as an example of how this method works when confronted with real mysteries rather than fictional secrets of conspiracy theories or pseudoscience. It is about real uncertainty arising when nature displays configurations we have not encountered before, which we must decipher through patient observation and thoughtful reflection. The question of tension remains relevant. What if the anomalies do not resolve naturally? What if the analysis confirms the absence of a tail? Spectroscopy reveals impossible isotopes, dynamic acceleration cannot be explained by evaporation, and the accumulation of evidence prompts contemplation of hypotheses currently deemed too exotic. When does the unusual cease to be natural? We need radically different explanations. Science does not have a predetermined threshold, only collective opinion formed through publications, peer reviews, debates at conferences, and the gradual building of consensus. Currently, the collective opinion leans towards natural explanations, but remains open to new data. If future observations ultimately refute the traditional behavior of comets, if tail formation becomes impossible under any structure, acceleration incompatible with the physics of sublimation, and materials require technologies we do not possess, then opinions will change. Not quickly and not easily, but eventually inevitably, because the strength of science lies in its self-correction and willingness to reconsider data. At this moment, Atlas 3I occupies the border space between the ordinary and the unusual, between the explainable and the mysterious, between patience and impatience. It urges us to accept uncertainty, resist premature conclusions, and maintain intellectual humility in the face of complexity. These disciplines are not easy in a culture that craves quick answers and definitive statements, but they are necessary for those who want to understand how we truly comprehend the universe, rather than how it seems we do. Synthesis, thus, is based on openness to evidence, to revision, to surprises. Atlas III may be a natural comet of exotic origin with unusual but possibly explainable properties, or something even stranger, which we can only understand after accumulating new data and expanding our theoretical frameworks. An honest answer is that we do not yet know everything. We are working on it, and it is precisely in such uncertainty that science thrives most vividly. Part 15. Global Consequences, Risks, and What to Pay Attention to. Each scientific observation has consequences beyond its immediate field, radiating ideas and influencing related areas of knowledge, sometimes touching on issues we did not expect to encounter. The three-dimensional object, 3I Atlas, regardless of how its anomalies are ultimately resolved, has already generated ideas worth discussing. This concerns the science of comets, populations of interstellar objects, the diversity of planetary systems, and even the unlikely possibility of detecting technological artifacts through astronomical observations. If Tri-I Atlas turns out to be completely natural, its significance will remain substantial. This will demonstrate that interstellar comets possess a diversity in composition and behavior that exceeds that observed in solar system comets, reflecting a wide range of formation conditions throughout galactic history. This diversity will confirm the hypothesis that each planetary system is unique, shaped by the metallic composition of stars, the chemical composition of disks, the migration history of giant planets, and many other variables that differ from system to system. Astronomy will receive a richer classification of cometary objects, expanding from categories focused on the solar system to galactic schemes considering low-metal objects, carbonaceous objects, ancient processed objects, and other categories yet to be imagined. This extension will be useful for comet physics, providing natural experiments. Objects formed in different conditions will test our model's predictions about how composition affects activity, how dust properties depend on formation chemistry, and how sublimation dynamics vary with the ratio of volatiles. Every well-characterized interstellar guest will become a data point refining theories, gradually transforming the science of comets from descriptive to predictive, from interpreting individual cases to a reliable statistical foundation. If the anomalies persist and cannot be explained naturally, the consequences will be much more significant. The constant absence of a tail during active exhaust will force a reconsideration of dust production mechanisms, possibly revealing new physics of particle aggregation or electrostatic effects not accounted for in modern models. Straight-line acceleration, incompatible with sublimation, will indicate forces we have yet to identify. Perhaps the connection to the solar wind is more effective than expected. Perhaps magnetic fields interact with the ionized coma in unexpected ways. Perhaps radiation forces on asymmetric bodies create unpredictable accelerations. All these phenomena will remain natural, but will expand our understanding of what the concept of natural includes, adding complexities and nuances to the frameworks we considered mature. Science progresses through such expansions, each anomaly ultimately resolved through deeper understanding rather than a rejection of natural laws. The history of astronomy is full of examples. The existence of Neptune was inferred from the anomalous orbit of Uranus. Dark matter was hypothesized to explain the rotation curves of galaxies, and dark energy was introduced to account for cosmic acceleration. Anomalies lead to discoveries if approached with rigor and creativity. The most significant consequences may arise if the Atlas of Three Eyes turns out to be artificial, although this is unlikely given the existing data. The discovery of technological artifacts would be the most important breakthrough in human history, instantly answering the question of whether we are alone in the universe and raising many new questions about the prevalence, nature, and fate of technological civilizations. These consequences will affect all areas: science, philosophy, theology, politics, culture, as humanity will face confirmed existence of other intelligences. However, exceptional evidence is necessary, which currently does not exist. No geometric structures in high-resolution images, coherent electromagnetic emissions recorded by radio telescopes, or materials that cannot be formed naturally have been observed. The dynamics that violate conservation laws or demonstrate controlled propulsion have not been recorded. Until these phenomena are confirmed as artificial in origin, their existence remains speculative entertainment rather than a scientific hypothesis. The risks of such an investigation are mainly related to reputation and resource allocation. Overestimating the possibility that the Atlas of Three Eyes could be artificial, in a situation where evidence does not support this, may lead to public disappointment when more mundane explanations emerge. Frequent wolf cries teach people to ignore legitimate future discoveries, creating situations where genuine breakthroughs are dismissed as just another hype. Scientists must balance openness to unexpected possibilities with the responsibility to honestly report probabilities and the quality of evidence. Resource allocation also poses a risk. If the Atlas of Three Eyes receives disproportionately much attention and time from telescopes relative to its actual scientific value, other worthy projects suffer. Astronomy operates under conditions of limited resources, limited observation time, funding, and personnel. Every hour spent observing the Atlas of Three Eyes is an hour not spent on characterizing exoplanets, studying the evolution of galaxies, observing supernovae, or many other research endeavors. The decision regarding the priority of Atlas Three Eyes must be based on scientific merits rather than public interest or speculative possibilities. At the same time, underinvestment also carries risks. If the Atlas of Three Eyes is indeed an anomaly requiring intensive study, a lack of observations may lead it to leave our area of interest before key measurements are completed, leaving gaps in our knowledge. The object will not return. Interstellar visitors pass by once and will not be seen again. Missing the opportunity to comprehensively characterize it will be a failure of scientific priorities, a capitulation to resource limitations when the stakes justify exceptional efforts. The upcoming checkpoints are clear. The Pagelian Pass offers maximum activity and the best conditions for observations. JUICE images provide a different geometry of view and tool capabilities. Long-term astrometry ultimately determines the dynamics. Spectroscopy, hunting for isotopic signatures and molecular species. Polarimetry clarifies the properties of dust. Each checkpoint will either resolve anomalies, confirm them, or transform them into new questions requiring further observations. What should society pay attention to? The clear formation of a tail would signal typical behavior, placing the three-eyed Atlas object in an interesting yet natural category. A persistent absence of a tail, despite maximum heating, would deepen the mystery, forcing creative explanations. Isotopic ratios confirming ancient origins with low metal content would support the hypothesis of a thick disk and explain the composition features. Anomalous isotopes, possibly deuterium relationships incompatible with the known stellar environment, would raise profound questions about origin and nature. Spectroscopic detection of complex organic compounds could hint at prebiotic chemistry, intriguing astrobiology, even without confirming the presence of life. The discovery of simple geometric structures in enhanced images would provoke intense study, although natural processes can create surprisingly geometric shapes, such as hexagonal craters, linear cracks, and regularly spaced jets, so geometry alone could not prove artificial origin. Radio wave emissions and abnormal frequencies showing modulation patterns incompatible with plasma physics would indeed be unusual and require immediate follow-up study and independent verification. Most likely, the resolution will be gradual and unsatisfactory. No observation will definitively resolve all questions, but the accumulated evidence will slowly shift the consensus towards natural explanations that consider the features of the three eyes of Atlas without requiring exotic hypotheses. The tail may appear faint in later observations, explained by delays due to surface crusts. The composition may be interpreted as typical for thick disk objects when we study more of them. Polarization may correspond to updated models that take into account ancient radiation processing. The story will not end with a loud finale, but rather with a quiet conclusion, an interesting footnote in comet catalogs rather than a revolutionary discovery. But there is always a possibility, however remote, unlikely, yet not zero, that the three-eyed Atlas is indeed something beyond our current understanding. This possibility, though minor, justifies the attention, study, and resources dedicated to its comprehension. Because if we are mistaken in considering it natural, if the anomaly turns out to be controllable, if evidence begins to accumulate, forcing us to consider exotic alternatives, then the consequences will extend beyond astronomy. We will encounter evidence of intelligence beyond Earth, that technologies spread between the stars, that we are part of a broader cosmic community, which we have only partially glimpsed thanks to this singular, strange visitor. The final monologue takes us back to the beginning. The first image of the European Southern Observatory should not look like this, without a tail, compact, and mysterious. Here it is, the three-eyed Atlas, pixels arranged in unexpected patterns that nonetheless fit within a wide range of possibilities. Perhaps this is the essence. Perhaps the universe, through the three-eyed Atlas and many other anomalies, is trying to tell us that our models are temporary, our understanding incomplete, and our categories too rigid to encompass the fullness of reality. Perhaps the right answer lies not in forcibly fitting observations into existing frameworks or immediately jumping to exotic explanations, but in accepting the mystery, patiently exploring, and remaining open to everything that may arise from careful study. The three-eyed Atlas continues its journey, racing through the inner solar system at 86 kilometers per second, ignoring our research, debates, hopes, and assumptions. It will pass perihelion, possibly flaring with activity or remaining angular and tailless, then retreat to the outer solar system and eventually return to interstellar space, rejoining the slow cycle of matter between the stars. We will observe until it disappears from sight, extracting every photon of information, every spectral line, every dynamic constraint, and then we will wait for the next visitor. The fourth confirmed interstellar object, pondering whether it will behave as expected or add new mysteries to the growing collection. This anticipation is our reality now, between visits, between observations, between hypotheses and confirmations. It is uncomfortable, but honest, uncertain, but thrilling, disappointing, yet intellectually vibrant. This is how science works, how knowledge grows, how humanity learns about the universe that refuses to simplify for our convenience. The three-eyed Atlas teaches patience, humility, and wonder, offering no final answers but posing questions that linger, observations that astonish, and the constant possibility that sometimes, just sometimes, reality is stranger and more wonderful than we could imagine.